In this lesson, we want to talk about the vertex form of a parabola. So we've already spent a lot of time working with quadratic functions, but we want to specifically learn how to graph a quadratic function. And in order to do that efficiently, we need to know about this vertex form, okay? So we're going to talk about that today. In case you're clueless about what a vertex is, we'll talk more about it in the next lesson when we're graphing. But basically, the vertex of a parabola is the lowest point if it's an upward-facing parabola, right? You get that standard U shape. And then it's the highest point if it's a downward-facing parabola. So if it's a U turned upside down. Again, we'll talk more about this in the next lesson. For now, we need to know how to convert between this form and this form. So something like f of x equals a times x squared plus bx plus c, where a is the coefficient for x squared, b is the coefficient for x to the first power, and c is your constant term. Now, most textbooks, most people will say this is standard form. This is going to vary based on which textbook you're using. Some textbooks will say this is standard form. So I don't want to confuse you, but I'm going to refer to this as standard form and this is vertex form. Okay, so this guy right here, this f of x equals, you have your a times the quantity x minus h squared plus k. The reason most people say this is vertex form is that you can immediately, upon inspection, find out where the vertex is. So the vertex will occur at h comma k. So this is my x coordinate, okay, and this is my y coordinate, right? So this would occur at h comma k. This would be my vertex for the parabola. So what we need to understand for today's lesson is how to go from this format here, this f of x equals x squared plus 12x plus 34 into vertex form, right? This is what I call standard form. We want to go into that vertex form, that f of x is equal to a times the quantity x minus h, and this is squared, and then plus k. So I want you to notice something. This is a binomial that's squared. So we know earlier in the course we talked about the fact that if you have a binomial squared and you go through the forward process, you get a perfect square trinomial, or a three-term polynomial that factors into this guy right here, a binomial squared. Remember, we can create this guy from the completing the square process. I know a lot of you guys are probably rusty on this, so let me just walk you through it. The first thing you need to make sure of is that the coefficient on the x squared here is a 1. So in this case, that's already done for us. Okay, so you don't need to do anything there. We'll see an example in a minute where it's not, but for right now, it's super easy. So the next thing you want to do is group your x squared term and your x to the first power term together. So I'm going to say I have f of x is equal to x squared plus, I have this 12x. So I'm just going to put parentheses around this for right now to say this is just in a group, and then plus my 34. Okay, so what I want to do now is complete the square. And let me just scroll down and get some room going. So I'm going to say I have f of x is equal to, I'm going to make this a little bit bigger, so x squared plus, I have my 12x, and then I'm going to add something here to complete the square, and then I'm going to subtract something here, and I'll explain this in a minute, and then I'll put plus 34 like this. Okay, so do you remember how to get this missing term right here? Remember, you take the variable that's raised to the first power, and you take the coefficient of that variable. So in this case, it's 12, right? That's the coefficient. You cut it in half, meaning you multiply by half, and you square it. So 12, if I cut that in half, or if I multiply by half, that's 6. 12 times 1/2 is 6. If I squared that, I would get what? I would get 36. Okay, so this is what I need to create my perfect square trinomial. So I'm going to add 36 right here. But I can't just do that. Normally, I would add 36 to both sides to make that legal. But in this case, I want this f of x over here on the left. I don't want to mess with that. So what I'm going to do is I'm going to subtract 36 as well. So 36 minus 36 is 0. I haven't changed anything mathematically. I can always add 0 to something. It's not going to change anything. So what I want to do now is close the parentheses down on this, okay? But normally, you have something out here that's multiplying this, and this creates an issue. Here, I just have parentheses here, so I can, at this point, just close the parentheses off like this and remove this from here, and I haven't done anything mathematically illegal. You have to be careful, though. If you have something out here that's multiplying this, then you've got to distribute, and we'll see an example of that in a moment. So for right now, what I've got is a perfect square trinomial here. So f of x equals, I can factor this into what? Well, it would be x plus, again, this guy was 6. Okay, so x plus 6, that quantity squared. And then over here, I just do negative 36 plus 34. That's going to give me negative 2. So I've found my vertex form. It's a little bit off, okay, but you can still write it this way. Remember, we said the vertex form was f of x equals a times the quantity x minus h squared plus k. So the reason I say it's a little bit off here is because of the signs. Here you have a plus and here you have a minus. Here you have a minus and here you have a plus. So if you want to define the vertex, you'd have to write it in this format or just know how to convert it off the top of your head, which most people do. But essentially you would just take this and say, okay, I'm going to match the format. So a is 1, so you don't need to write anything there. You can just say x minus a negative 6 is the same thing as plus 6. So now I have matched that minus sign there, okay? So minus a negative 6, and then this is squared, and then I'm going to do plus a negative 2, okay? So from here now I can just grab this guy right here and this guy right here, and I know my vertex occurs at negative 6, comma, negative 2. Okay, so that would be my vertex for this parabola. All right, let's look at another one. So this one will be a little bit more challenging because the coefficient on x squared is not 1. So we have f of x equals 2x squared plus 32x plus 123. So again, the first thing you have to do is make sure that this guy is a 1. Now, again, when you work with this, when you're solving quadratic equations by completing the square, you just divided everything by 2. But you don't want to do that, again, because you have this f of x over here. You don't want to mess with that. So what you're going to do now is you're going to factor it, okay? So I'm going to say that I have f of x is equal to, I'm going to factor a 2 out from this, again, first group. I'm going to treat these as a group, and I'm going to say I have 2 times the quantity. I'd have x squared there, and then plus, if I pulled out a 2 from there, I'd have 16x. Okay, so I've taken care of that. Okay, and let me just kind of scooch this down. I know I've got to add something and subtract something. And let me put my parentheses there, and let me put plus 123 there. Okay, so what are these two missing values here? Again, I just take this guy right here, this coefficient, look at the variable raised to the first power, we want that coefficient, cut it in half and square it. Okay, if you just say that a few times, you'll remember it forever. Cut it in half and square it. My 9th grade algebra teacher taught that to me, and I never forgot it. So if I cut 16 in half, I get 8. If I square 8, I get 64. So if I say 64 here and 64 here, okay, I have completed the square, but this is where it gets a little tricky and a lot of people make mistakes. Normally, if this guy isn't here, if this isn't a 2 here, I can just regroup this, okay? But because there's a 2 here, you got to realize that to remove the parentheses, we have to use the distributive property and multiply 2 by every term there, okay? But I don't want to do that. I just want to get rid of this part right here. So what I'm going to do is say that I have f of x is equal to, I'm going to keep my 2 out in front, so times the quantity x squared plus 16x plus 64. And then for this part right here, I'm just going to distribute the 2 to this so that I can remove it out of there, okay? And I'm going to say I have plus, and I'll do 2 times this negative 64. And then I'll wrap this up by saying it's plus 123, okay? So that's what you got to be careful of, okay? If you have something outside the parentheses like this 2 or whatever the number is, if it's not 1, you've got to do this extra step. It's a very common mistake to miss that. All right, so now what we want to do is write this. We'll say f of x equals 2 times the quantity. Okay, this guy would factor into what? It's x plus, we know that 64 came from us taking 8 and squaring it, so this would be 8, and this would be squared, and then we would have 2 times negative 64, which is negative 128, and then plus 123. We know that a negative 128 plus 123 would be negative 5. So this would be your vertex form. You have f of x equals 2 times the quantity x plus 8 squared and then minus 5. Again, if you want to match things up perfectly, you would write this as minus negative 8, okay? And you would write this as plus a negative 5. So I could just write that like that and say f of x is equal to 2 times the quantity x minus a negative 8, again squared, and then plus a negative 5. So the vertex here is going to occur at negative 8 and then comma negative 5. So negative 8, comma, negative 5. Again, this is your vertex. Okay, let's just do one more, and then I'll go into the super simple vertex formula, which is what you're going to use, but you might need to know how to do the completing the square method. It's always good to look at it because it comes up every so often. All right, so we have f of x equals 11x squared plus 66x plus 90. I'll kind of go through this very quickly. We know we want to factor that 11 out. So what I'm going to do is say this is f of x is equal to, I'm going to treat this, again, first 2 as a group. So 11 times the quantity x squared plus 6x, and then plus 90. Again, I'm just factoring the 11 out from the first 2 terms. All right, so let's go ahead and say this guy right here, I want to cut that in half, okay? Again, you're looking at the variable raised to the first power. Look at the coefficient. cut it in half and square it. Cut it in half and square it. So 6 divided by 2, or 6 times a half, is 3, and then 3 squared is 9. So what I'm going to do is I'm going to add 9. Okay, I'm going to add 9 inside of the parentheses. Now, if you wanted to get really advanced, I recommend just putting minus 9 inside of here so you remember to distribute. But if you can remember this on your own, you can just say that, okay, I have 11 times negative 9, okay? So it would be minus 99 out here. Okay, so I just kind of skipped a step there. Once you do this a few times, you're going to skip that step. You just have to make sure that you multiply 11 by the negative 9 so that it's the correct number. So then we have our plus 90 here, and we're ready to go. So what I can do is I can very quickly factor this and say this is f of x is equal to 11 times the quantity. This guy factors into what? X plus the 9 came from 3 squared, so 3, this quantity squared. And then negative 99 plus 90 would be minus 9. Okay, so that's your vertex form. Again, if you wanted to match it up perfectly, you would want this to be a minus and this to be a plus. So you'd say f of x is equal to 11 times the quantity x minus a negative 3. This is squared, and then plus a negative 9. So your vertex occurs where? Negative 3, comma negative 9. So the vertex, okay, the vertex is going to be at negative 3, comma negative 9. All right, so now let's talk about the vertex formula. And this is something that you're basically going to use. You're not going to complete the square every time. You're just going to do that if you're asked to do it. So we have this f of x equals ax squared plus bx plus c. Okay, again, you got to know that a is the coefficient for x squared, b is the coefficient for x, and c is the constant. We already know this from the quadratic formula, so it should be something that's familiar to you. And if you go through the process of completing the square to put this in vertex form, you would find that the vertex occurs at negative b over 2a, so this is your x coordinate, and then your y coordinate would be f of negative b over 2a. So in other words, find out what x is, and then once you have that, plug it in for x in your function, and you're going to get y as the result. So let's look at an example. All right, so here we have f of x equals 5x squared minus 20x plus 15. So if I wanted to find the vertex, what I would do is I would say that the x coordinate is negative b over 2a. So what is b and what is a? We know that a is the coefficient for x squared and b is the coefficient for x. Make sure you include any sign. So if it's minus, you want to put plus negative so you don't make a sign mistake. So the negative of negative 20 is 20. Okay, and then 2 times a is 5, so this is 10. So this is 20 over 10, which is 2. So the x coordinate is 2. And then what we want to do is plug this in for x to find out our y coordinate. So in other words, we want to just know what is f of 2. So we would have 5 times 2 squared is 4. And then plus, you'd have negative 20 times 2, which is negative 40, and then plus 15. So I'll do 20 plus 15, which is 35, and then 35 plus negative 40 is negative 5. So this would be negative 5. So your vertex occurs at 2 comma negative 5. Okay, if you wanted to write this in vertex form, again, just match things up. It's f of x equals a times the quantity x minus h squared plus k. So h, again, is going to be your x coordinate. So this is the x coordinate, and k is your y coordinate. And I'm going to run off the screen, so let me kind of scooch that down. Okay, so what we want to do here is say that we have what? We have f of x equals, what's my a? What's this, right? It's the 5. So 5 times the quantity x minus, what's my h? It's the x coordinate. So from the vertex, my x coordinate is 2, and this quantity squared, and then plus, we have my y coordinate, which is k, okay? So this is negative 5 in this particular case. So I can put plus negative 5 if I want, or I could just put minus 5. It doesn't really matter. So the vertex form here is f of x equals 5 times the quantity x minus 2 squared, and then minus 5. All right, let's just do one more of these. It's good to get a lot of practice because when you start graphing these things, you need to know how to do this off the top of your head. All right, so we have f of x equals negative 4x squared minus 64x minus 261. Again, the vertex will occur at negative b. B in this case is negative 64. So the negative of negative 64 is positive 64 over 2 times a. A is negative 4. 2 times negative 4 is negative 8. So 64 over negative 8 is negative 8. So the x coordinate is negative 8, And then again, to get the y coordinate, I want to do f of negative 8. So what is that? Well, negative 8 squared is 64. 64 times negative 4 is negative 256. And then you would have negative 64 times negative 8, which is positive 512. And then lastly, you'd have minus 261. So if you do negative 256 plus negative 261, you get negative 517. And then negative 517 plus 512 would, of course, be negative 5. So let's just go ahead and say this is negative 5. So we'll put negative 5 there. And I'll just go ahead and erase this. And again, if you wanted to write this in vertex form, you'd say f of x is equal to your a, which in this case is negative 4, times the quantity x minus whatever your x coordinate is from the vertex. In this case, it's negative 8. So you could put minus a negative 8 or you could put plus 8. It really doesn't matter. So this quantity is squared. And then you're going to have your plus k. K, again, is the y coordinate from the vertex. So this is negative 5. So you can put plus negative 5 or minus 5. It doesn't really matter. So your vertex form is going to be f of x equals negative 4 times the quantity x plus 8 squared and then minus 5. In this lesson, we want to talk about graphing parabolas. All right, so in the last lesson, we talked about the standard form and the vertex form of a parabola. We learned how to convert back and forth between the two. So again, I'm going to define this first one here, f of x equals a times x squared plus b times x plus c. I'm going to say this is standard form, and I'm going to say this guy right here, f of x equals the a times the quantity x minus h squared plus k. I'll say that's vertex form. Based on your textbook, it might be different. They might call this guy right here standard form, but I'm going to stick to calling that vertex form. So I don't want you to be confused by that. Now, when we talk about the vertex of a parabola, once again, it's the lowest point on an upward-facing parabola, or it's the highest point on a downward-facing parabola. Now, when we have our quadratic function in vertex form, what's special here is that we can get the vertex by just looking at the equation. So the vertex will occur at h comma k. So this is your x coordinate and this is your y coordinate. You can just pull it straight from here. So as long as it's in the minus form here and the plus form here, you just take your h and you take your k. Now, if you have different signs there, you have to make an adjustment for that, and we'll see that later on in the lesson. Now, let's kick things off by looking at a parabola that we've already seen before. So this guy is the simplest type of quadratic equation that you're going to come across. It is the f of x equals x squared that we already saw when we're talking about graphing transformations, okay? So we already know the points. We know that there's 0, 0, there's 1, 1, negative 1, 1, so on and so forth. 2, 4, negative 2, 4, and then 3, 9, negative 3, 9. You could do 4, 16, negative 4, 16, again, so on and so forth. Now, a couple of things to kind of pay attention to here. You can see that the vertex here occurs at 0, 0, okay? And if you wanted to write this in vertex form, you could play around with it and just say it's f of x is equal to, well, the a here, the coefficient of x squared is 1, so you don't have to put anything there. You would just say x, in this case, minus 0, that quantity squared, and then plus 0. Okay, and you're just doing this to show that this guy would be the x coordinate, and this guy would be the y coordinate, so the vertex would occur at, again, 0, 0, and that is your lowest point. Now, let's move on and talk about something else that's important when you look at a parabola. This vertical line that I've drawn in here that's basically going over the y-axis is known as the axis of symmetry, or you might also hear people say the line of symmetry, okay? So basically what this is, it's a line, and it's a vertical line to be specific, that intersects the vertex. So this guy is always going to be a line that is x equals whatever h is, okay? So again, h is the x coordinate of the vertex. In this case, it's 0. So this line here would be x equals 0, which is just the y-axis in this particular case. But basically what this guy does is it divides our parabola into two perfect halves. So I could take a point on one side of the parabola. Let's just say we took this point here, which is 3, 9, and I could fold it across that axis of symmetry, and I would touch this point exactly, which would be negative 3, 9. And we'll see this comes in handy when we're graphing, because if we get points on one side, we can kind of reflect them across that axis of symmetry and get points on the other side. All right, so now let's get into graphing a quadratic function, or you could say graphing a parabola. Basically, this is a very simple process. It only gets hard if the coefficient of this guy right here is a fraction, okay? If it's a whole number or an integer or something like that, it's very, very easy. I'm going to show you 3 different ways you can do this. The second method I'm going to show you is the quickest, but let's start out with kind of one of the more challenging methods, which is using graphing transformations. So in order to do this, we'd want to first write this in vertex form. So how do we do that quickly? Again, vertex form is f of x equals, if you got your a times the quantity x minus h, and this is squared, plus k. Well, again, a is the coefficient for x squared. In this case, that's 1. So if this is a 1, you can just get rid of that, okay? So what's h and what's k? Well, in the last lesson, we talked about a shortcut to figure that out, right? We saw that we could complete the square to get this, or there's a quick and easy formula we can use. So the vertex formula tells us that h occurs at negative b over 2a. Again, this is your a, the coefficient for x squared. This is your b, the coefficient for x to the first power. And this is your c. Okay, you don't need c here in this particular case, but I'm just labeling it for reference sake. So what is negative b over 2a? Well, b is 6, so I would have negative 6 over. For a, I have 1. So negative 6 over 2 times 1, which is 2. So this is negative 3. So this is the x-coordinate, okay, the x-coordinate for the vertex. So my vertex here will occur at negative 3, comma, and let me just put this in here. If I put minus a negative 3, that would be fine, or I can put plus 3 if you want as well. It doesn't matter, okay, as long as you know this is negative 3 for that coordinate. Okay, so the way we get k is we plug a negative 3 in for x in our function. Okay, so in other words, k is going to be equal to f of negative 3. And so we say we'd have x squared. So we'd plug in a negative 3 there. Negative 3 squared would be 9. And then plus 6 times negative 3, which would be negative 18. Okay, and then plus 8. Well, 9 plus 8 is 17. And 17 plus negative 18 is negative 1. So my vertex is going to occur at negative 3, comma, negative 1. So let's put minus 1 out here. Okay, so this is my quadratic function in vertex form. Okay, so we know the vertex is here. We know this is here. But in this particular case, we don't even need the vertex. We just need this guy here because we're going to use our graphing transformations. Okay, so we start out by comparing it to f of x equals x squared. Okay, so what do we have here? What happens inside? Well, we add 3. Remember, when you talk about what happens inside the function, you do the opposite. So if it's plus 3, you're shifting to the left by 3 units. So we would say that this guy is going to shift left 3 units, okay? And then this guy right here is happening outside the function. So this is your vertical shift, okay? And that's straightforward. If you have minus 1, I'm just shifting down by 1 unit. So we'll say shift down 1 unit. So we shift left 3 units and we shift down 1 unit. Okay, so we can take that graph, f of x equals x squared. We can do these shifts and we'll have our new graph. So let's go ahead and see that real quick. So I've already drawn these side by side for you. So again, you can take a point like this. This is 0, 0. You can go 1, 2, 3 units to the left and 1 unit down. I'm going to use a different color there. Let me use like a light or a dark blue. How about that? And let's just take this point here. So you go 1, 2, 3 units to the left, 1 unit down. Take this one, 1, 2, 3 units to the left, 1 unit down, so on and so forth. You can get this graph by, again, just applying shifts to the graph that you already know. So that's the first method. All right, let's talk about the easy method. This is the one that you're probably going to use in almost every case, unless you have a fraction as your value for a, in which case it becomes a little bit more challenging to use this guy. You might want to use a different method. All right, so again, we have this f of x equals x squared plus 6x plus 8. We already know that the vertex form is f of x equals 1 times the quantity x minus a negative 3, or you could say x plus 3, that quantity squared, and then plus negative 1, or again, you just say minus 1 if you want. So with this method, you basically want to find your vertex, which we already know it's negative 3, comma, negative 1. So your pattern is 1 times a, 3 times a, 5 times a, and 7 times a. Now in this particular case, again, a is the coefficient for x squared. It's right here and it's right there. It's implied there, okay? So we know a is 1, so 1 times 1 is 1. 3 times 1 is 3. 5 times 1 is 5. And 7 times 1 is 7. So this is the pattern. So first I would plot negative 3, comma, negative 1. So I'm going to go to negative 3, comma, negative 1. So that's right here, okay? And then I'm going to use that pattern, that 1, 3, 5, and 7. So what does this mean? basically what's going to happen here is I'm going to, as I move to the right 1 unit, I'm going to go up by this unit. So I'm going to go to the right 1, up 1, okay? Now the next time I go to the right 1, I'm going to use this guy right here. So to the right 1, up 1, 2, 3. Now the next time I do this, I'm going to go up 5. So to the right 1, up 1, 2, 3, 4, 5, okay? So you can continue. I'm going to go off my particular graph, but if you wanted to go to the right 1 and up 7, you could do that as well if you had enough room on your graph paper. So the idea here is that you can use that to get one side of the parabola. And again, your axis of symmetry here is x equals, again, what's the x coordinate for the vertex? Well, in this case, it's -3. So it's x equals -3. So that's your axis of symmetry. So I can use that to get these points on the other side. If I fold it across this line, just think about the fact from right here to right here is what? It's 1, 2, 3 units. So if I just go 1, 2, 3 units over here, there's my point, right? So here it's going to be 0, 8. And over here it's going to be -6, 8. Again, you could do the same thing with this point. You could take this and fold it across the line and get here. Take this, fold it across the line and get here. And then once you have enough points, you can sketch a pretty accurate graph. Let's talk about the third and final method that you can use, and then we'll just burst through a couple of problems. So again, we have the f of x equals x squared plus 6x plus 8, and in vertex form, the f of x equals 1 times the quantity x minus a -3 squared, and then plus a -1. Vertex occurring at -3, -1. We already know what this is. Now, in most textbooks, they're going to teach you to first find the vertex, which we have, and then they're going to tell you to find the x and y intercepts, and then they'll tell you to just grab additional points as needed. So you can use this method if you want. Again, it's in most textbooks. I found it to be pretty slow and inefficient overall, but we're going to go ahead and go through this just for the sake of completeness because your teacher might ask you to do this. So the first thing is, how do you get the y-intercept? Do you remember that's where you basically plug in a 0 for x, right? Because at the y-intercept, x is going to be 0 because you're crossing the y-axis. So in the standard form here on the top, I can just say, what is f of 0? Well, these two would be gone, and it would just be 8. So a point here, the y-intercept would be 0, 8. Okay, so that's something I would want to plot. Then I would find my x-intercepts. How do we do that? Well, we make y, or f of x, 0 now, because we're crossing the x-axis. So I would solve the equation, x squared plus 6x plus 8 is equal to 0. Okay, again, if you just replace this with y, and then you replace y with 0, this is nothing more than what we've been doing all along throughout all of algebra. And we come down here and we solve this by factoring. It's very, very easy to solve this guy. So this guy would factor into what? X here and x here. I've got two integers that sum to 6 and give me a product of 8. That would be 4 and 2. So plus 4 and plus 2. So the solutions here would be x equals -4 and -2. Okay, so that tells me that the x-intercepts are going to be at -4, 0, and then also at -2, 0. So let's erase all this. And again, we could just plot these points. And let me just paste this in here real quick. And I'll write this more neatly. So we have 0, 8. We have -4, 0. Let me make that better. And of course, we have -2, 0. Okay, so let's erase this. All right. So we know the vertex occurs at -3, -1. So -3, -1. We have our axis of symmetry. Again, that's x equals -3. And then we just plot these points. So we have 0, 8. So 0, 8 is here. And you can reflect this across the axis of symmetry to get this point over here, this -6, 8. Then you have your two x-intercepts. So you have your -4, 0 and your -2, 0. So you don't get these 2 points from this method. Okay, so you'd be sketching the graph with just these 5 points, which can still give you a pretty accurate sketch of what's going on. In most cases, these things, your teacher's not asking you to be perfect. Just give them an accurate sketch of what's going on. We know in this day and age that we can pull up any graph from an online calculator in a millisecond. So the idea is just to show that you know how to perform this task. Okay, let's look at 2 more problems, and I'm going to do these using the quick and easy method because in most cases, you're just going to do this. Again, unless you get a fraction for this value here for a, right, you can use this method. It's very, very effective. So we have f of x equals 2x squared minus 8x plus 6. So the first thing I want to do is put this in vertex form and grab my vertex, and then I want to think about that pattern, okay? So I would have f of x is equal to, again, a times the quantity x minus h, this is squared, and then plus k. So what is h? What is k? We know a is 2, right? It's the coefficient of x squared. So let's put a 2 in there. And again, for my h is equal to negative b over 2a. Well, what is negative b? Well, b is this guy right here. Include the sign, so negative 8. So the negative of negative 8. So make sure you don't make a sign mistake. You've got a negative there. You've got a negative 8 there. So the negative of negative 8, which would be positive 8, over 2 times a. A in this case is 2. So the negative of negative 8 is 8. So that's 8 over 2 times 2 is 4. So this is 2. Okay, so this guy would be 2. And that would be the x-coordinate for our vertex. So let me erase this real quick. And let me write this over here. So the vertex, we already know the x-coordinate is at 2. And then what about my y-coordinate? Again, to find that, I just plug a 2 in for x in my function. So what is f of 2, right? This would give me my k. This is what? It's going to be 2 squared, which is 4, times 2, which is 8, minus 8 times 2, which is 16. So let me just go ahead and write that. Let me just put minus 16. And then plus 6. So negative 16 plus 6 is going to be negative 10. And if I did 8 minus 10, that's negative 2. So this is negative 2. This is negative 2. And again, I can put plus negative 2, or I can just put minus 2. It doesn't really matter. Now, what I want to do now is just grab my vertex. So 2 comma negative 2. So my vertex is 2. Let me make that better. So 2 comma negative 2. So 2, negative 2. That's going to be right there. My axis of symmetry is x equals 2. So you see that line is already drawn. And basically what I want to do now is just use my pattern. Okay, so remember it's 1a, 3a, 5a, 7a, so on and so forth. Now, in this particular case, a is not 1. So you have to be careful because you can kind of think about this as 1, 3, 5, 7 for the easy examples when a is 1, but when a changes, you've got to pay attention. So if we come back up here, remember a is 2. It's the coefficient for x squared. So when we come back down here, the pattern's going to change. 1 times 2 is 2. 3 times 2 is 6. 5 times 2 is 10. 7 times 2 is 14. So what this is telling me is that when I move to the right 1 unit, I've got to go up 2 units. So to the right 1, up 2. Okay, so that's a point. Then if I move to the right 1 unit, I've now got to go up 6 units. So to the right 1, up 6. So that puts me there. Now, again, I'm going to run off the graph, but if I went to the right 1 unit, I would need to go up 10 units now to get to my next point on the graph. Now, we don't need this because, again, I'm off my particular graph, but if you were using some kind of long graph paper, then you can go through and get as many additional points as you want using this method. So I've got 3 points here, and I'm just going to reflect across this axis of symmetry to get this point here, right? Because again, the distance from here to here, this is 1, 2 units away. So this is going to be 1, 2 units away. From here to here, this is 1 unit away. So this will be 1 unit away. Again, you just reflect across that axis of symmetry to get those other points, and then you can draw a sketch of that graph. Let's do one more of these. I think it's useful to look at an upside down parabola. So we have f of x equals negative 2x squared minus 12x minus 16. So again, write it in vertex form. So f of x is equal to a times the quantity x minus h squared and then plus k. All right, a is negative 2 here. So let's go ahead and write that in. So we'll say this is negative 2. And then what's my h, what's my k? We already know that h is what? It's negative b over 2a. So what's b? b is negative 12. So the negative of negative 12 is 12. Over 2 times negative 2, which is negative 4. So this is going to be negative 3. Okay, so again, minus a negative 3 is plus 3. So you can put plus 3 in there if you want. But remember, when you write the vertex, when you say this is the vertex, you've got to put it in as negative 3. So negative 3. All right, so let's erase this. What is k? K is equal to what? It's f of whatever this guy was. Again, you're not putting in a positive 3. You're using this coordinate here, which is negative 3. So f of negative 3. These are just common mistakes, things that you'll find yourself doing when you first start, when you're not really paying attention. So you got to pay close attention to the signs. So f of negative 3 is what? Well, we'd have negative 3 squared, which is 9. 9 times negative 2 is negative 18. And then you'd have a negative 12 times a negative 3, which is plus 36. And then you'd have minus 16. Okay, well, 36 minus 16 is 20. And then if you did negative 18 plus 20, that's positive 2. Okay, so this is going to be 2 here. So let's write this down here. So it's negative 3 comma 2. So negative 3 comma 2. Again, that's my vertex. And let's go ahead and write this as a 2 right there, like that. So let's go ahead and plot negative 3 comma 2. So we would have negative 3 comma 2 is right there. So that's your vertex. Then again, your axis of symmetry is going to go through that vertex. So we would say this is x equals, the x coordinate is negative 3. So x equals negative 3 is the axis of symmetry. Okay, so again, the step pattern is what you want to have. So you have 1a, 3a, 5a. In this particular case, you don't need to keep writing these out because you're only going to get 2 additional points out of this because my graph only goes down to negative 10. Okay, so we know a, if I go back, is negative 2. Again, it's always the coefficient of x squared. So 1 times negative 2 is negative 2. 3 times negative 2 is negative 6. And 5 times negative 2 is negative 10. Okay, so what you want to do is say, okay, if I go to the right one, I'm going to go down by 2 because it's a negative 2. So to the right one, down 2. Now to the right one, the next one is negative 6. To the right one, down 6 units. Okay, so that puts me there. Again, if you wanted to go to the right one again, you would fall by 10 units to get to the next point. For myself, on this graph, I can't do that. I would run out of room. Okay, so I can only put these 2 points in. So it's very important to remember with this kind of pattern that, again, it's 1a, 3a, 5a, 7a, so on and so forth. Make sure you do the multiplication by a. Otherwise, you're going to get the wrong answer if a is not equal to 1. Okay, so you've got to pay close attention to that. We get lulled to sleep by these kind of easier examples where a is equal to 1. Then we get the harder examples and we don't know what to do, or we just get the wrong answer. Now, once you have these points over here, again, you can reflect them across this axis of symmetry. Again, this is 1 unit away, so this will be 1 unit away. This is 2 units away, so this will be 2 units away. And from that, you can have your graph. In this lesson, we want to talk about the remainder theorem. All right, so when you talk about the remainder theorem, it's basically just a shortcut for evaluating a function at a given value. So let me start out with this easier example, and then I'll explain what's going on. So we have something like f of x equals x cubed plus x squared minus 5x minus 12. And we want to start by asking, what is f of 3? So we know what this notation is. We've been working with functions forever. We know that this is just asking for us to plug in a 3 for each occurrence of x and find out what is the value of the function when that happens. So what is f of 3? I'm just going to plug in a 3 here and here and here. And so I would have what? 3 cubed is 27, and then plus 3 squared is 9, and then minus 5 times 3 is 15, and then minus 12. So this would give us what? 27 plus 9 is 36. 36 minus 15 is 21, and 21 minus 12 is 9. Okay, so this result here, we already know how to do this by plugging in. But there's another way that you can do this, and it comes from this remainder theorem. So let me go to a fresh sheet real quick. And I want to rewrite my polynomial. So we have f of x is equal to, we have our x cubed, and then we have our plus x squared, and then we have our minus 5x, and then we have minus 12. Okay, so with synthetic division that we talked about earlier in the course, you can take a polynomial like this, and you can divide it by a polynomial of the form x minus k. So remember, we had something like x minus k as our divisor, where the coefficient of x is 1, and it's raised to the first power. So it's got to be of this form. So this guy right here, when we talk about the remainder theorem, is what we're going to be plugging in for x in our function. In our example, we used 3. So for this guy, we would be dividing by x minus 3. So let me put this as the divisor. So let's just say g of x is equal to x minus 3 as an example. So if I do f of x divided by g of x, what would that look like? Well, I could do a polynomial long division, or again, because it's in this format, I can do a synthetic division, which is quicker. I just grab whatever this is, okay, and I put it over here in the top left, and then I want to put kind of a division symbol, or you can use whatever symbol you want, it doesn't really matter. And I'm going to grab just the coefficients from this dividend here. So this is a 1, this is a 1, this is a negative 5, and this is a negative 12. Now, you've got to make sure that these are in order, okay, in terms of the degree. So it's x cubed, x squared, x to the first power. You got to make sure it's lined up that way. And if you're missing a power of x, you put a 0 as a placeholder, okay? It's very important. So I'm going to take my 1 here and write it in, and then I've got a 1, I've got a negative 5, and I've got a negative 12. So I want to do the synthetic division here, and the idea is that when I do the synthetic division, our remainder is going to be 9, because that's what I found when I plugged a 3 in for x in my f of x earlier. We saw that already. So to do the synthetic division, I'm going to drop this down, and then I'm going to go through, again, we're going to multiply, then add, so on and so forth. So we say 3 times 1 is 3, then we add, 1 plus 3 is 4. Then we say 3 times 4 is 12, then we add, negative 5 plus 12 is 7. Then we multiply, 3 times 7 is 21, and then we add, negative 12 plus 21 is 9. So remember how this answer works. This guy right here, this leftmost position, is the coefficient for x raised to a power that is 1 degree less than this kind of polynomial that you're working with here as your dividend. So this guy has a degree of 3, right? That's the highest power. So this guy will have a degree of 2. So this is basically going to be an answer of x squared plus 4x plus 7, and then your remainder is 9. So typically we'd say plus 9 over the divisor, which was x minus 3, okay? So let me erase this already. We don't need this anymore. We already see that we got the same answer here, but I want to explain where this comes from. So let me kind of drag this up. And before we get into this, I want to just break this down as simply as I can. So I want to use an example first from just whole numbers. So when you were in elementary school, you did something like this. So 7 divided by, let's say, 3. So we know this result would not be just a whole number, right? 7 divided by 3 would be 2 with a remainder of 1. Okay, and we know that we could write this as 2 1/3, or we could punch it up on a calculator and we get a decimal form, but that's not important. We know the remainder is 1, so let's write it that way. Now, what we can do is we have this guy right here, which is the dividend. We have this guy right here, which is the divisor. We have this guy right here, which is the quotient. We have this guy, which is the remainder. So if I take the quotient, which is 2, and I multiply it by the divisor, which is 3, and I add the remainder to that result, I will get back my dividend. 2 times 3 is 6. 6 plus 1 is 7. Okay? So it's very important you understand that process with whole numbers before we do this with polynomials, because, again, once you understand it in its most simplest form, you can apply it to something that's more complicated. We're going to do the same thing here. So this guy right here is my divisor. Okay? So I have x minus 3, and then I multiply by the quotient, which is this part right here. Okay, so the quotient is x squared plus 4x plus 7. Okay, then I add my remainder to that. In this case, that's 9. Okay, so that's my remainder. So you have your divisor, you have your quotient, and you have your remainder. So it's the same thing that we looked at with the whole numbers a second ago. Now, you can pause the video and you can see that if you go through and simplify here, you will get this back exactly. Okay, but I also want you to notice that if you plugged in a 3, in this case, what would you get? Well, if I plugged in a 3, well, what happens is, because I have the minus 3 there, okay, 3 minus 3 would be 0, and 0 times this, whatever it is, x squared plus 4x plus 7, doesn't matter. I know I'm plugging in a 3, but forget about that for a second. 0 times this would just be 0. So this is gone. This is 0. So I'd have 0 plus 9, which is 9, okay? Again, that's exactly what we found from plugging a 3 in for x here, and also through the synthetic division. So that's why this works. To get a more general view, something you'll see in your textbook, they'll write this out and say, okay, we have f of x, and this is equal to, we'll have x minus k, which is your divisor, okay, times q of x, which is your quotient, plus r, which is your remainder. Again, if I want to find f of k, well, if I'm plugging in a k there, k minus k is 0. 0 times whatever this is 0. So I'm just left with my remainder r. So this is why this works. Okay, if you want to find f of some number, well, then you can just do synthetic division. Okay, so let's look at some more examples. And so for this one, we have f of x equals negative 5x to the 4th power plus 15x cubed minus 11x squared plus 6x minus 15. We want to find f of 2. And again, you could plug a 2 in there and do it that way, but this is going to be a bit quicker. So I'm going to put 2 here, and I'm going to set this up. So I'm just going to grab my coefficients. So negative 5, 15, you've got negative 11, you've got 6, and you've got negative 15. Okay, so let me put a bar down here. I'm going to drop my first number, and we're ready to roll. So 2 times negative 5 is negative 10. 15 plus negative 10 is positive 5. 2 times 5 is 10. Negative 11 plus 10 is negative 1. 2 times negative 1 is negative 2. 6 plus negative 2 is 4. 2 times 4 is 8. Negative 15 plus 8 is negative 7. So you just take this remainder, forget about everything else, and you say f of 2 is just negative 7. All right, let's go ahead and look at another one. So we have f of x equals negative 3x to the fourth power plus 9x cubed plus 4x plus 3. We want to find f of 3. Now, this is very important. Okay, people forget this all the time and they get the wrong answer. So if you're missing a power of x, so I started with the fourth power, then I have cubed, I don't have squared. Okay, got to write a 0 in as a placeholder. So pay attention. So I want to put something like 3, and then I'm going to put negative 3, 9. I'm going to put 0 here as a placeholder because I don't have an x squared. Then I'm going to put 4, and then I'm going to put 3. So negative 3, 9, 0 because I'm missing x squared, 4, and then 3. Okay, so make sure you do that. Otherwise, you will not get the right answer. All right, let's drop this down. So we have negative 3 here. 3 times negative 3 is negative 9. 9 plus negative 9 is 0. 3 times 0 is 0. 0 plus 0 is 0. 3 times 0 is 0. 4 plus 0 is 4. 3 times 4 is 12. 3 plus 12 is 15. Okay, so my remainder here is 15. So f of 3 is 15. So you might also get some examples with complex numbers. These are more tedious. So typically you see a degree of 2, maybe a degree of 3 if your teacher is, wanting you to spend some time on it. This is no more difficult, but you do need to understand how to work with complex numbers. We've already seen this earlier in the course, so I'm confident that you can get through this. So suppose we had f of x equals x squared minus 2x minus 3. We want to find f of 2 plus I, okay? So again, you just set this up the same way. So you put 2 plus I over here. Grab your coefficients. So you have a 1, you have a negative 2, and a negative 3. So let me scroll down. We're going to need some room for this. So let's drop this down here. So if I had 2 plus I times 1, I would have 2 plus I. So here's where it gets a little tricky. So you need to add these two numbers. So let's say we have negative 2 plus you have this 2 plus I. So you're just going to add the real parts. So negative 2 plus 2 is 0. So I'm left with just I. Okay, so this is just going to be a result of I. So now what I have is multiplication. So 2 plus I times I. So I'll just do I on front times 2 plus I. So I times 2 is 2i, and then plus I times I is I squared. Now, remember by definition, I squared is negative 1, so we're just going to write minus 1 here, okay? And I'm going to flip the order because that's the way you write it. So negative 1, and then plus my 2i. Okay, so let me put this up here. So negative 1 plus 2i. Now, my last step is to add, and what I'm going to have is negative 3, and then we have plus this negative 1 plus 2i. Again, add the real parts. Negative 3 plus negative 1 is negative 4. And then this plus 2i would come along for the ride. So this is my remainder, this negative 4 plus 2i. So that would be my f of 2 plus I. All right, so let's talk about a related concept here. And to get an idea of what's going on, let's just start with something simple like, let's say f of x equals, let's just do x squared minus 9. So we already know that when we work with functions, if I replace f of x with, let's say, y, and I replace y with 0, what am I doing here? I'm finding the x-intercept, right? The x-intercept occurs when y is set equal to 0. We already know that. So I'm solving for x. This is where we would cross through the x-axis, okay? So to solve this is very easy, right? So I would say 0 is equal to, I'm going to factor this into x plus 3 times x minus 3. We know this is the difference of squares. We know this is x equals 3 and negative 3. Okay, we already know that. But basically what I want you to understand is that if I go back to this in its f of x form, so let's say we have f of x. Now if I plugged in a 3 there or a negative 3 for x, the result would be 0, right? So if I said, what is f of 3? Well, this is 0. What is f of negative 3? Well, this is also 0. So if I plug something in for x and I get a result of 0 for the function's value, meaning I've found the x-intercept, we call this a 0, a root, a solution. There's a lot of different names for it, but I'm just going to stick to calling it a 0 for now. So if we plug something in for x in our function and it gives us a 0 as a result, we call this a 0. We'll talk more about this in the next lesson. All right, so let's just look at one example of this. It's a very easy concept. So we have f of x equals x to the fourth power minus 4x cubed minus 4x squared plus 25x minus 12. We're asking, is 3 a 0? In other words, would the point 3, 0 be on the graph of this function? Would it be an x-intercept? One of them. So what we would do is just use synthetic division to see if this is true or not. So we put a 3 here, and then we set this up as we normally do. So we'd have a 1, we'd have a -4, we'd have another -4, we'd have a 25, and then we'd have a -12. Okay, drop this down, and then we can get started. So I have a 1 here, and 3 times 1 is 3. -4 plus 3 is going to be -1. Then 3 times -1 is -3. -4 plus -3 is -7. 3 times -7 is -21. 25 plus -21 is 4. 3 times 4 is 12. -12 plus 12 is 0. So there's no remainder here. So yes, we can say that 3 is a 0 or a solution or a root for this function. In this lesson, we want to talk about the factor theorem. All right, so before we get into talking about the factor theorem, I want to make sure that you understand the remainder theorem, which was what we talked about in the last lesson. So if we have some polynomial function, let's call it f of x, okay? And it's divided by some linear factor, so let's call this x minus k. Again, the coefficient on x is 1, and the exponent on x is 1. So that's very important. So it's some linear factor, we call it x minus k when we think about this generically. Now, if I divide f of x by x minus k, the result will be some quotient, which we call q of x, plus some remainder, which we call r. So we can rewrite our polynomial function f of x in this way. So we have this divisor x minus k times our quotient q of x plus our remainder r. Now, if this doesn't make any sense to you, we'll look at an example in a minute. And also, let me just give you a quick example with some whole numbers so that it makes more sense. So let's say that you had the number 7 and you divided it by the number 3. So 7 is your dividend, 3 is your divisor, the quotient is 2, okay? But then you have a remainder of 1, okay? So what we would say here is that I could write 7 using this format as what? Well, my divisor here is x minus k, my divisor here is 3, okay? Then times, my quotient here is q of x, my quotient here is 2. Then plus, my remainder here is r, my remainder here is 1. So it's quite simple when you look at this with whole numbers. We have our divisor, 3, times our quotient 2, which is 6, plus our remainder 1, which gives us 7. Okay, so that's all we're really doing. It's the same thing. We just got to find a way to relate this to a harder concept when we work with these polynomial functions. Now, the reason this is important to write it in this format is that it makes it crystal clear about the remainder theorem, which tells us if we evaluate a polynomial function at some number, let's just call it k, so f of k is how we would notate that, the result is r. And the reason for this is simple. F of k is equal to, again, if I plug in a k for x, you'd have k minus k times q of k plus r. Well, this is 0. So you can erase this and put 0 here. 0 times whatever this is 0. So you can erase this. And 0 plus r is just r. So f of k equals r. That's what this tells us here, and that's the remainder theorem. Okay. So to see a quick example, let's look at this guy real fast. We have f of x equals x cubed plus 2x squared minus 21x plus 18. If we want to find out what is f of 2, well, of course, you can plug a 2 in everywhere there's an x, evaluate, and you've got your answer. But you could also say, well, what is the remainder from dividing this guy by, let's say, g of x is x minus this number here, whatever it is. So x minus 2 in this particular case. So the remainder from that would be the same as f of 2, okay? So the way we're going to do this is with synthetic division. So I'm going to put a 2 here. Whatever this number is, that's what you put there. And then I'm going to grab these coefficients only. Remember, if you're missing a power of x, you got to put a 0 in there as a placeholder. So I'm not missing any powers there, so I'm good to go. I'm just going to grab my coefficients. This guy's a 1, this guy's a 2, this guy's a -21, and this guy's an 18. Okay, so you remember how to do this. Draw a little bar down here. Go ahead and drop this down. I'm going to scroll down and get some room. I'll come back. So drop this down. So now we're going to multiply. 2 times 1 is 2. Then we add. 2 plus 2 is 4. Then we multiply. 2 times 4 is 8. -21 plus 8 is -13. So then we multiply. 2 times -13 is -26. And lastly, we're going to add. 18 plus -26 is -8. So this is your remainder. And so that tells me that f of 2 is -8. But what we can also do is take this answer here. This would be your quotient, right? And the way you get this is that our polynomial, let me just scroll up real quick. I'm just going to erase this and keep the answer part. Let me just bring this up here so it's all on the same screen for us and come back up here. I had this guy divided by this guy. So we always know it's of the form x minus k. So to take these numbers and make sense of them, all you do is you take this degree of the polynomial, in this case the highest exponent is a 3, this would just be 1 less. So this is the coefficient for, in this case, it would be x squared, because 3 minus 1 is 2. Okay, so 1 would be the coefficient for x squared. Then you would have plus your 4x, and then minus your 13. Okay, so this would be your quotient. So let's erase this real quick. We know the remainder is negative 8, but again, I could write this. Let me just kind of scooch this down so we can really draw this point home. So f of x could be written as this times this divisor here. And I can change the order around. It doesn't really matter. And then we can put minus 8 here. Okay. So if you pause the video and you go through and multiply this by this and then subtract away 8 from that, you'll get back to this exactly. Okay. Now, if you think about what is f of 2, again, when it's in this format with the divisor times the quotient plus the remainder, you see clearly you just get the remainder, because if I plugged in a 2 there, 2 minus 2 is 0. 0 times whatever this is 0. I'm left with just negative 8. So again, we say f of 2 is negative 8. So hopefully that drives home what the remainder theorem is and how it works. Now, let's move on and talk about the factor theorem, which again, if you understand the remainder theorem, is very simple. So if f of x is equal to x minus k, again, our divisor, which is a linear factor, times this q of x, which is the quotient, plus r, and we find that f of k equals 0, well then what? It means that this times this gives me this, right? There's no remainder, or a remainder of 0. Okay, so that tells me that x minus k is a factor of f of x. We also know from the last lesson that if f of k equals 0, then k is known as a 0, or you could say it's a root or a solution, or really they're the x-intercepts if you're talking about k being some real number. Now, let's look at a couple of examples. Let's say that we have the same f of x, but we're going to change our value for k. In this case, it's going to be 3. So f of x again is x cubed plus 2x squared minus 21x plus 18. Now we want to know what is f of 3. If f of 3 is 0, then we can say that x minus this value, x minus 3, is a factor. Okay, so let's see what f of 3 is. So I'm going to say 3 here, and I'll take my 1, my 2, my negative 21, and my 18. Let me get some room going just so we're not jammed up on here. Drop this down and get started. 3 times 1 is 3. 2 plus 3 is 5. 3 times 5 is 15. Negative 21 plus 15 is negative 6. And then 3 times negative 6 is negative 18. 18 plus negative 18 is 0. Okay, so the remainder here is 0. So that tells me, since f of 3 is 0, that x minus, again, whatever this number is, in this case it's 3, x minus 3 is a factor. Okay, so x minus 3 is a factor of this guy right here. Okay, so let's scroll down and look at a couple more problems here. So we have f of x equals, we have x cubed plus 4x squared minus 22x plus 20. So we have g of x equals x minus 2, and we just want to know, is this a factor? Okay, so again, you just take this number right here. As long as it's in the format of x minus some number. If it's not in this format, you got to change it to where it's x minus some number. We'll see an example of that in a moment. But basically, I can, again, just take 2, put it out here, and then grab my coefficients. So 1, 4, negative 22, and 20. And I'm just going to see, is the remainder 0? If it is, then x minus 2 is a factor. If it's not, then x minus 2 is not a factor. So let's go ahead and drop this down. 2 times 1 is 2. 4 plus 2 is 6. 2 times 6 is 12. Negative 22 plus 12 is negative 10. 2 times negative 10 is negative 20. 20 plus negative 20 is 0. So there's no remainder here. So I can say, if we kind of go back up here, that x minus 2 is in fact a factor, right? Because we can say that f of 2 is equal to 0. All right, let's take a look at a longer one. So we have f of x equals x to the 5th power plus 2x to the 4th power minus 6x cubed minus 12x squared minus 16x minus 32. Is g of x, which is equal to x plus 3, is that a factor? Again, you want this in the form of x minus k to make this work. you have a plus there. If you see that, you've got to change it. Okay, it's a very common mistake to just put 3 out there and then to get the wrong answer. Okay, so you want to make sure you change this and just say this is equal to x minus a negative 3, so that it's in that format, and then you grab whatever this number is. Minus whatever this number is, that's what you're going to say. So is f of negative 3 equal to 0? So that's a question mark. Again, we're just going to use some synthetic division. So I'm going to say that I have negative 3, grab my coefficients. I've got a 1, a 2, a negative 6, a negative 12, a negative 16, and a negative 32. And a lot of these problems are going to get quite tedious, so you just have to be prepared for that. Okay, so let's scroll down, get some room going. Let's drop this to here. Negative 3 times 1 is negative 3. 2 plus negative 3 is negative 1. Okay, so negative 3 times negative 1 is going to be 3. Negative 6 plus 3 is negative 3. Negative 3 times negative 3 is 9. Negative 12 plus 9 is negative 3. And then negative 3 times negative 3 is 9. Negative 16 plus 9 is negative 7. And negative 3 times negative 7 is 21. Negative 32 plus 21 is going to give me negative 11. So this is not 0. Okay, this is not 0. So f of negative 3 is negative 11. And so I can say that this g of x, which is x plus 3, or you could say x minus a negative 3, is not a factor of f of x. Okay, let's look at the same f of x, but we're going to change kind of our divisor. We're going to call it h of x now, and now it's x plus 2. So same thing. In this case, it's plus, so change it to x minus a negative 2. Very important you do that. Again, it's a common mistake. I can't say that enough. So you want to take your negative 2, and again, just see if the remainder from this guy is 0. So we would have a 1, a 2, a negative 6, a negative 12, a negative 16, and a negative 32. Okay, so that's everything. So let's go ahead and scroll down a little bit. Okay, so let's go ahead and drop this and get started. So negative 2 times 1 is negative 2. 2 plus negative 2 is 0. Negative 2 times 0 is 0. Negative 6 plus 0 is negative 6. Negative 2 times negative 6 is 12. Negative 12 plus 12 is 0. Negative 2 times 0 is 0. Negative 16 plus 0 is negative 16. Negative 2 times negative 16 is going to be 32. Negative 32 plus 32 is 0. So that's your remainder. It's 0, right? Meaning you don't have one. So that tells me that x plus 2 is a factor, right? So you can say h of x is a factor of f of x. All right, so let's look at another common problem that occurs in this section. So basically what's going to happen here is they're going to give you one factor and they expect you to find the other ones, okay? So we have f of x equals x cubed minus 7x squared plus 14x minus 8, and our factor is x minus 2. So what that means is that if I plugged in a 2 for x, so if I had f of 2, this is 0, right? They're telling us that, okay? So what I can say is that if I plug in a 2 there, and I do my synthetic division, so I have a 1, a negative 7, a 14, and a negative 8. I'll do this, I'll get a remainder of 0, and I'll take that quotient, and then I'll try to factor that further, okay? So let's go ahead and crank this out. So I'll drop this down. 2 times 1 is 2. Negative 7 plus 2 is negative 5. 2 times negative 5 is negative 10. 14 plus negative 10 is 4. 2 times 4 is 8. Negative 8 plus 8 is 0. Okay, so I don't need this part. And again, when we think about this, if I go back up, this guy has a degree of 3. So the answer will have a degree of 2. So if I erase this, I'll say that my answer here is just x squared, and then minus 5x, and then plus 4. Okay, so that's how this would go. So this times this would give me this, right? I could say f of x is equal to this, right? We already know that. Now, let's think about factoring this guy. So this is a quadratic, very easy to factor. So we have x here and x here. And we need two integers that sum to negative 5 and have a product of positive 4. So we can get negative 4 and negative 1, right? Because negative 4 times negative 1 is 4. And then negative 4 plus negative 1 is negative 5. So negative 4 and negative 1. And let me write that in a more compact manner. So I'm just going to say f of x here is equal to x minus 4 times x minus 1 times x minus 2. In this lesson, we want to talk about the rational zeros theorem. So when we work with polynomial functions, we're often asked to find the zeros. So let's say you came across f of x equals 3x cubed minus x squared minus 3x plus 1. And let's say your teacher asks you to find the zeros. So we already know that a zero or a solution or a root is something that when we plug in for x in our function f of x, we get a result of 0. So how could we find the zeros here? So there's going to be a lot of different methods you're going to come across. The one we're going to focus on today is known as the rational zeros theorem, or some people call this the rational roots test. Now, let me explain what this is. The rational zeros theorem is just going to give us the possible candidates, okay, so it's not necessarily true that they're going to work, for rational zeros of a polynomial function with integer coefficients. So let me be clear here. The polynomial function you're working with has to have integer coefficients, and this method is only going to give you possible rational numbers to check, okay? So it's not necessarily true that they're going to work. Now let's think about what a rational number is so that we're all on the same page. In pre-algebra, we define these as P over Q, where we say Q is not equal to 0, and P and Q are both integers. So something like 2/3, right? Something like the number 5, because we could say 5 over 1, so on and so forth. So if I could put one integer over another integer to form a number, that's a rational number. So something that's not a rational number would be like the square root of 2. Right? In decimal form, it does not terminate, it does not repeat the same pattern, so it's not a rational number. Also, if you think about numbers that are involved with the imaginary unit I, we think of those as a complex number, so those would not be involved here as well. So when you generate this list, you're only looking at rational numbers, so I want to be clear there. Now, what you want to do to kind of get things going, you want to make sure that your polynomial, let me just erase this, is in standard form. So f of x equals, we have 3x cubed minus x squared minus 3x plus 1. So this is in standard form because the highest exponential power is all the way to the left. Okay, so that's how you want it. Then the next highest, then the next highest, right? So on and so forth. So there's two terms you're going to hear. The first thing is the leading coefficient, and the second thing is the constant term. So the leading coefficient is the coefficient on the variable that is raised to the highest power. Again, if it's in standard form, this is all the way to the left. So in this case, that's going to be a 3 because the highest power here is a 3. So that's my leading coefficient. So it's 3. Then you're also going to talk about the constant term. So this is your term, if it's in standard form, all the way to the end, and it doesn't have a variable involved. So this is your constant term. Now, the way this is going to set up, if this number P over Q is some rational number, and let's say it's written in lowest terms, so there's no common factor other than 1 between P and Q, then if it's going to be a 0 of your polynomial function, let's call it f of x, then P is a factor of our constant term. Okay, so P would be a factor of 1. So in this case, 1 only has positive 1 and negative 1 as factors. So let me just say plus or minus 1 there. And then for Q, it's going to be a factor of our leading coefficient. So in this case, it's 3. So 3 is a prime number, so that would be plus or minus 1, and then plus or minus 3. So you've got to include all these kind of different signs. So you do plus or minus 1 for the P, and then for Q you have plus or minus 1 and then plus or minus 3. So the way you want to do this is you want to go through the different possibilities that will occur. So how I would set it up, and you don't have to do it this way, but I just take whatever's in the numerator. Okay, so I would start with 1. A lot of times you have more than just one number here, but I would just take 1, and then I would go over each denominator. So the way I would do this is I would just take my plus or minus, and I would say that I have 1 over 1. Okay, so that's just plus or minus 1. Then I would take my 1 again, make sure to put the plus and minus out in front, and I would go over the next guy, so it would be plus or minus 1/3. Okay, so that's how you can do this really quickly. If you're wondering about the signs, because a lot of people get confused with these signs, you're only going to have two possibilities here. Okay, even though you really have 4 numbers between here and here, right? Because you're thinking about, okay, I have 1 over 1, and then I have negative 1 over 1, and then I have 1 over negative 1, and then I have negative 1 over negative 1. But think about how fractions work. If it's a positive over a positive or a negative over a negative, like you have here and here, well, that's a positive. So that gives me the positive 1. And then if it's a negative over a positive or positive over a negative, that gives me the negative, right? So that's why you can just shortcut this. You don't have to go through everything. You can just put plus or minus, okay, plus or minus, and then just take your number part there over the number part here, and you're basically going to be good to go. Okay, so don't even worry about the signs. So we've generated 4 possible rational solutions. You've got 1 and -1, you've got 1/3 and -1/3. So if we wanted to, at this point, say what works, you can use synthetic division, or you can straight up just plug things in, which in this case is probably faster, and you can see if the result is 0. Okay, so I can say, is f of 1 equal to 0? If it is, then 1 is a 0. Is f of -1 equal to 0? Is f of 1/3 equal to 0? Is f of -1/3 equal to 0? You know, so on and so forth. Now, I'm just going to pause here for a minute. As we go through these examples, I'm not going to do these each time because in some cases it's going to be ridiculous. Okay, you need other tools to make this kind of method work for you. We'll get to those tools in future lessons. So for right now, we just want to focus on understanding the rational roots theorem. So very quickly, let's test these and see which ones work. So what I can do is say, what is f of 1? Well, if I plugged in a 1 here, here, and here, well, 1 to any power is just 1. And if I multiply 1 by a number, I just get the number. So really, I can just kind of mark these out and say I'd have 3 minus, this would be a 1, right? So 3 minus 1 is 2. And then 2 minus 3 is -1. And -1 plus 1 is 0. Okay, so that's 0. So we know that 1 is a 0 of this polynomial function. What about -1? Well, let's just go through and say this is 3 times -1 cubed. Then we have minus, you'd have -1 squared. Minus 3 times -1, and then plus 1. We can simplify this really quickly. We know this is -1, so I'll just put a negative out in front. This right here would be +1, but you have a negative out in front. And then this would be +3. Okay, so let's go through. We have -3 plus 3, which is 0. -1 plus 1, which is 0. So this is 0 as well. So f of -1 is 0. Let's check 1/3. So again, we would just plug in a 1/3 everywhere there's an x. So you'd have 3 times, you'd have 1/3 cubed, which is 1 over 27. If you simplify this, 3 and 27 have a common factor of 3. So this is 1/9. Then minus, if you had 1/3 squared, that would be 1/9. And you can just stop right now and say 1/9 minus 1/9 is 0. So just erase that. So basically you have -3 times 1/3 plus 1. We know this would cancel and give me a 1. So this is -1 plus 1, which is 0. So this works as well. Now, as we move through this section, you're going to find that for this polynomial, because this highest exponent is a 3, it can only have at most 3 distinct zeros. Okay, so we've already met that, so we could stop. We know that this guy wouldn't work. But we haven't gotten to that yet. We're going to get to that in a future lesson. So let's just check this real quick. We'll see that it doesn't work. So we would have 3 times -1/3 cubed would be -1 over 27. Again, we can cancel the 3 and the 27. So let's just say this is a 9 down here. And then you'd have minus if you had 1/3 and it's negative and it's squared. Well, the negative goes away. 1/3 squared is 1/9. So you'd have minus 1/9 there. Okay, and we can go ahead and do this and say this is going to be overall -1 minus 1, which is -2. So this is -2/9. And then you have your minus 3 times -1/3. So there you can think about the signs canceling because you're going to have a -3 times a -1/3. So let's put plus. And 1/3 times 3 is 1. And then you have plus 1. So to get a common denominator, I'll say this is 2. And 2 times 9 over 9 would be 18 over 9. And so -2 plus 18 is 16, so this is 16/9. Okay, so we see this is not 0. So we know that this is not a solution, right? This -1/3. So not a solution, not a 0, not a root. So even with this very simple example, you can see how tedious it was to go through and find the zeros. Now, other things you can do, once you have 1 0, again, you can use this with synthetic division to find the factors of this guy. So you could factor this guy. And then once you have it in the state where you have x minus 1 would be one factor, and then you'd have another factor. Well, this guy right here, this other factor would be a quadratic. You could use a quadratic form if you wanted to. So there's all kind of techniques that we can use. And again, we'll talk about those as we progress through this section. Let's look at two more examples. I'm not going to see if the roots work here. I'm just going to go through and list the possible rational zeros. So I have f of x equals 5x cubed plus 54x squared plus 24x minus 7. Again, I want to find all the p over q, those possible rational zeros, okay? So p comes from the factors of your constant term. So in this case, it's -7. Don't worry about the sign because you're always going to do plus or minus anyway. Just think about what are the factors of 7? Well, it could be 1, it could be 7, it could be -1, it could be -7. So really you just put plus or minus 1 and then plus or minus 7. Okay, so that's what you're going to put for that. Then for q, again, that comes from the leading coefficient. So the leading coefficient, again, if this is written in standard form, it's all the way to the left. The highest power in x is a 3, so the leading coefficient is a 5. So in this case, for 5, you have plus or minus 1, and you have plus or minus 5. So I'm giving you another easy example, but you're still going to see that there's a lot of possibilities here if you wanted to go through and check stuff. So I'm going to take my plus or minus and put that first. And then again, I just take this number and go over this number. So plus or minus 1 over 1 is 1. Then I'm going to go plus or minus, I'm going to take this number, and I'm going to go over this number. So plus or minus 1 over 5, which is plus or minus 1/5. Now I'm going to move down, and I'm going to take this number and go over this number. So let me write this down here so I have enough room. So plus or minus, don't forget that. You have your 7 over 1, which is just 7. And then lastly, plus or minus, I'm going to shift this down and say you have your 7 over 5. So plus or minus 7/5. Okay, so this gives us what? We have 1, 2, 3, 4, but then times 2 because you have a plus or minus in each case. So we have 8 possible rational zeros. Now, I'm not going to test these. It's just way too much work. But if you're curious, 1/5 is the only rational zero that we have here. All right. I want to wrap up the lesson and just look at one more of these. Again, we're just trying to get the concept down. We're not really trying to get zeros at this point. We'll do that as we progress. So we have f of x equals 3x cubed plus 7x squared plus 15x minus 14. So what are the possible rational zeros? So again, just think about p over q. And again, when you think about p, it's coming from the factors of this constant term here. So just think about 14. Again, forget about the fact that it's negative. 14 is what? It's 1 times 14 or 7 times 2. So you would have plus or minus 1. You would have plus or minus 2. You'd have plus or minus 7 and then plus or minus 14. Now, let's think about q. That comes from, again, factors of your leading coefficient. So in this case, that's going to be 3. 3 is a prime number. So you're just going to have plus or minus 1 and plus or minus 3. So again, I've given you easy examples, and you're going to see that even with these easy examples, the list becomes really, really big. So if you get something that's harder, you're going to have a really big list and a lot of different possibilities to check. So on its own, this rational roots test or rational zeros theorem is not very efficient. Okay, so you need other tools. So let's go through and figure out our possibilities. So again, I would go ahead and say that I have plus or minus. I'm going to take this number and go over these two. So 1 over 1 would be 1. And then plus or minus 1 over 3 would be 1/3. And then I'm just going to move down. So I'm going to say that I have plus or minus. I'm going to have 2 over 1, which is 2. And then plus or minus 2 over 3, which is 2/3. And then let me move down. So I'm going to have plus or minus. I'm going to have 7 over 1, which is 7. Let me come down here. So let me put my plus or minus. And then I'll have 7 over 3, which is 7/3. And then lastly, I'm going to come down here. And I'm going to have 14 over 1, so plus or minus 14. And then I'll have plus or minus my 14 over 3, or 14/3. So again, an easy example, and you see how quickly it gets out of control. You have 1, 2, 3, 4, 5, 6, 7, 8 times 2, so 16 possible rational zeros. And if you went through and checked all these, you'll find that 2/3 is the only one that works. And again, at this point, we don't have enough information to effectively use this technique. In this lesson, we want to talk about the fundamental theorem of algebra. All right, so as we continue to talk about finding zeros of polynomial functions, we're going to come across the fundamental theorem of algebra, which basically tells us that every polynomial function of degree n will have n complex roots, but we're going to see some of these may be repeats. So let me cover a few things real fast before we continue. I want to make sure you understand what I just said. So let's look at something like this. So f of x equals, let's say, x cubed minus x squared plus, let's say, 2x minus 1. We should all know that this polynomial function is of degree 3, right? We think about the highest exponential power on our variable. In this case, that's going to be a 3. So the degree of the polynomial is a 3. So that's what we're talking about when we say that. Now, with our fundamental theorem of algebra, this tells us that we would expect to have 3 complex zeros. But again, some of these might be repeated. And I'll show you an example of this in a moment. For right now, I just want to focus on the words complex zeros. What does that mean? Remember, when we work with numbers, specifically when we say complex numbers, they're of the form a plus bi. So if I had the number 5, most of you would not expect for that to be a complex number because it's just the number 5. But remember, a number like 5 can be a part of more than one set of numbers. 5 is a natural number. It's a whole number. It's an integer. It's a rational number. I could say it's 5 over 1. It's a real number. And it's also a complex number because I can say this is 5 plus 0 times I. Okay, so all the real numbers that you work with are also complex numbers. So when you start reading things about complex solutions, you're including things that you think of as real numbers in that. Okay, so let's erase that now that we have that point is clear. Now, when we talk about this fundamental theorem of algebra, basically what they're saying, and this is the setup here, you go back to the factor theorem, you say if x minus k is a factor of f of x, we know f of k is 0, right? So there's no remainder. This means if I divide f of x, my polynomial function, by this x minus k, I get some q of x, some quotient, okay? And that's all there is. There's no plus r over here. There's no remainder. So these two multiplied together give me this. Now, what this guy tells us is that, let's say I have f of x, and this polynomial function is of degree 1 or more. So you have an x involved or whatever the variable is, it doesn't matter. And the exponent on it is a 1 or higher. Okay, so it's not something like f of x just equals the number 5. That wouldn't work. So if this guy is involved, again, 1 or higher for the degree, then you'll always be able to find at least one complex zero to where you can say this is x minus, I'm just going to say this is k sub 1, because this is going to be my first complex zero, times q sub 1 of x, okay? So you can write it like this. Then, if this guy right here, you just keep this process going. If this guy right here is of degree 1 or higher, then again, you can always find at least one complex zero. So you just keep the pattern going, okay? So I can just say that this would be times x minus k sub 2. And again, I can just keep this going. So I can end up with just x minus k sub n. In the end, you're going to have a quotient that's just going to be a number. Now, that number might be 1, right? So it might be true that these guys just multiply together to give you your polynomial function, or there might be some number here. So we typically say this is a, and this would be put out in front. So let me put this out in front here, and I'll change my color. Okay, so that's how you end up with this form that you see in your book. So I want you to remember this for later because we're going to use it when we write some polynomial functions. I want to look at two examples to explain what we mean when we say that some of the complex zeros might be repeats. Let's start out with something really easy. So we have f of x equals x squared plus 3x minus 10. And again, we already know how to find the zeros for something like this. We've been doing it forever. So let's say x squared plus 3x minus 10. Let's set this equal to 0. If we factor this to solve it, put an x here and an x here, and we know we want two integers that sum to 3 and give me a product of negative 10. Well, that would be what? It would be positive 5 and it would be negative 2. 5 times negative 2 is negative 10. 5 plus negative 2 is positive 3. Okay, so the solutions here, or the zeros, would be x is equal to negative 5 and positive 2. So f of negative 5 would be 0 and f of 2 would be 0. Now, this is exactly what we expect because this polynomial function is of degree 2, right? That's for every quadratic function. Now, let's look at this case here, which you might remember will only have one solution, but we're going to say that it has a multiplicity of 2 because it's going to occur twice. So we have our f of x equals x squared minus 8x plus 16. Again, I'm going to solve this. So x squared minus 8x plus 16 equals 0. So you can factor this into a binomial squared, but what I'm going to do, just for demonstration purposes, I'm going to say this is x and this is x, minus and minus. So two integers that sum to -8 and give me a product of positive 16, well, it's going to be -4 and -4, right? -4 plus -4 is -8. -4 times -4 is positive 16. Okay, so the solution here is obviously x would be 4, right? So 4 is your only 0. F of 4 would be 0, but it occurs twice, right? Because you have two factors of it. So that's what the fundamental theorem of algebra is telling us. It's saying that you're going to have two zeros here, but one might be repeated. All right, so there's not much to this section. You just need to understand what the fundamental theorem of algebra is telling you. Additionally, you might be asked to write some polynomial functions based on the information that you're given. So what we're given here is 3 zeros. So we have 5, 4, and -4. And we have a point here. We have f of 1 equals 120, or in other words, you have 1, 120 that's on the graph of this function. Now, how could we write this polynomial function? Well, again, if I go back and I think about this form here, I would take this guy and I would just start substituting information in. So let me go back down. So what do we know? We know that there's a 0 of 5, there's a 0 of 4, and there's a 0 of -4. Now, with these problems, they're typically going to give you some instructions that say that they want a specific degree. In this case, we'd be looking for a degree of 3 because it gave us 3 zeros. Sometimes it'll tell you give them the minimum degree required to write the polynomial. Okay, so you might see it either way. But here we're looking for a third degree. Okay, so I know that 5 is a 0, 4 is a 0, and -4 is a 0. So if 5 is a 0, meaning f of 5 equals 0, then that means x minus whatever this is, so x minus 5, is my factor or my divisor, okay? Then I do the same thing here. I'm going to have x minus 4, and then I'm going to have x minus a -4, which is x plus 4. So I have f of x is equal to a times this. So this is what I got to figure out, and then I can go through and simplify. So how do I get this? Well, I'm going to use this point here. So basically, I know if I plugged in a 1 everywhere there's an x, the result would be 120, okay? So let's scroll down for a minute, and I'm just going to plug this in. So f of 1 is going to be equal to 120. So let's just go ahead and say we have a times 1 minus 5 is -4. And then 1 minus 4 is -3. And then 1 plus 4 is 5. And this should equal 120. So -4 times -3 is 12. 12 times 5 is 60. So you would have 60a equals 120. To solve for a, I would divide both sides by 60. And I would find that a is equal to 2. Okay, so let's erase all this. We will have everything. So a real simple process, just tedious overall. So now what you want to do is go through and just simplify. So if I want to kind of leave multiplying by 2 till the end, that's fine. Or you can do it at first, it doesn't matter. I'm just going to multiply everything together and leave 2 off till the end. So x times x is x squared. And then my outer would be minus 4x. My inner would be minus 5x. So together it would be minus 9x. And my last would be plus 20. Okay, so you'd have that times this. And let me come down here, get some room going. So I would have x times x squared, which is x cubed. I'd have x times negative 9x, which is minus 9x squared. X times 20, which is plus 20x. And then I have 4 times everything, so you'd have plus 4x squared minus 36x. And then you would have plus 80. Okay, so what does this give me? I'll put my 2 out in front. I've got x cubed, nothing to combine with that. Negative 9x squared and 4x squared would give me minus 5x squared. And then 20x minus 36x would give me minus 16x. And then lastly, I have plus 80. Okay, so now I'm just going to multiply everything by 2. And let's scroll down and get some more room going. So I'll have 2x cubed minus 10x squared minus 32x plus 160. Okay, so you can just box that off. This is going to be your polynomial function. Again, you can just put f of x. We have it all the way up there, but I don't want to scroll all the way back up. So f of x equals, again, this 2x cubed minus 10x squared minus 32x plus 160. Okay, let's look at one more of these. Another easy topic that you come across. So the zeros, you have 1, but it says it's got a multiplicity of 2, and then you also have -3. So again, this is going to be a third degree polynomial because, again, we're dealing with two zeros here. You have the 1 that occurs twice, and then you have another one which is -3. So you count that as 3 zeros, so you would have a degree of 3. Then we're told that f of -1 is 24. Okay, so let's write this part out first. So you'd have f of x equals, you'd have your a times, you'd have x minus 1. And this occurs twice. So you can put squared like this, or you can write it out and say x minus 1. And then you have x. Again, if you have a -3, it's going to be x plus 3. Okay, so we've got that part done. And now I just need to figure out what a is. So again, if I plugged in a -1 for x, so if I had -1 minus 1, that would be -2. If I had -1 minus 1, that would be -2 again. If I had -1 plus 3, that would be 2. So I know this is positive 8. So I can go ahead and just say that I would have 8a is equal to, the result would be 24. Divide both sides by 8, and I get that a is 3. So this is 3. Okay, so we got that done pretty quickly. And basically what we want to do is just simplify again. So I'm going to say that x minus 1 times x minus 1, that's going to be what? It's x squared minus 2 times this guy times this guy. So 2 times x times 1 is 2x. And then plus, we'll just go ahead and say that's -1 times -1 is 1. Okay, so we've got that. Let me put my 3 out in front so I don't forget it. And this is going to be multiplied by this. Okay, so let's go down here and let's go ahead and continue. So we have 3 times. So x times x squared is x cubed. Then x times -2x is minus 2x squared. Then x times 1 is plus x. And you have 3 times everything, so I'm just going to go plus 3x squared minus 6x and then plus 3. Okay, so let me just combine like terms inside first. So we have 3 times x cubed, nothing to do with that. Then we have -2x squared plus 3x squared. That's going to give me plus x squared. We have x minus 6x, which is minus 5x. And then we have plus 3. Okay, so almost out of the woods. Just one more step. We have 3 times all of this, so we would have 3x cubed plus 3x squared minus 15x plus 9. And again, the f of x part is all the way up there, so let me just kind of scroll down, and I'll rewrite it. So we'll just say that f of x is equal to 3x cubed plus 3x squared minus 15x plus 9. In this lesson, we want to talk about the conjugate zeros theorem. All right, so as we continue to talk about finding the zeros of a polynomial function, we're going to come across this section in our book that talks about the conjugate zeros theorem. So the conjugate zeros theorem, which is also known as the conjugate pairs theorem, just tells us that if we have a polynomial function, let's just say it's f of x, that has only real coefficients, then if some complex number, let's say a plus bi is a 0, then a minus bi, its conjugate, is also going to be a 0. So in other words, complex zeros always occur in pairs, okay? So if I had something like, let's say 2 plus 3i, and that was a 0, well, then it would also be true that 2 minus 3i would be a 0, okay? Remember, for conjugates, this part stays the same, okay? So you have 2 and 2, and then this part stays the same, so you have 3i and 3i. It's just that your signs are going to be different, okay? So you have a plus and then a minus. And we already saw this when we worked with quadratic equations, right? We would solve them, and we would find what? That you either had 2 real solutions, you had 2 complex solutions, meaning they were imaginary solutions with the imaginary unit I involved, or you would get one solution, but we already learned that we could say it has a multiplicity 2, right? It's the same solution that occurs twice. So those were your only 3 possibilities. So what we're going to do is use this information. We have 2 different tasks that we're going to complete in this section. The first one, we already talked about this in the last lesson. Basically what we're going to do is we're going to find a polynomial of least degree having only real coefficients and zeros that meet this criteria. So the zeros given are 1 and 1 plus 2i. So we know that this guy right here, this 1, that's just a regular 0. We've been working with that forever. But when we get this complex 0, 1 plus 2i, Well, we know that it's going to have its conjugate as a 0 as well. So we can go ahead and write in here that another 0 would be 1 minus 2i. Again, the 1 stays the same, the 2i stays the same, just change the sign to get the conjugate. That's all you're doing. So now if I want to write out my polynomial function, remember the form. It's f of x is equal to, it's a times you have your x minus k sub 1 times your x minus k sub 2, and then, you keep going, and then you have your x minus k sub n. Okay, so in each case, it's x minus whatever this 0 is. So in this one, I'd say x minus 1. And then for these, it's going to be a little bit more complicated because I'm subtracting away a complex number. So let me just kind of write this off here. And I'll say that this is x minus, and I'll put it in parentheses, 1 plus 2i. And then let me close that, and I'll do x minus, now I'm going to do 1. Let me slide this down. I'm going to run out of room. And now we'll have minus 2i. Go ahead and close that off. Okay, now in this particular case, you're not given any information. I know in the last section we were given a point, and then we could figure out what a is. So here a is just going to be 1, so you can just erase it or put a 1 there. And what happens is we're just going to go through and simplify this. It's going to take a little bit of time because it is quite tedious, but we'll have our polynomial function, and it's a good exercise to kind of practice working with these complex numbers. Okay, so let's go through and start simplifying. So I'll say f of x is equal to, I'm going to leave this for last. So I'm going to have x minus 1 outside of, and I'll just put some brackets here. And the way I'm going to do this is I'm going to do FOIL with these guys as they are, okay? So I'm going to treat this as the first term and this as the second term in each polynomial. So this is your first term, and this is going to be your second term, okay? So I'm going to say that I have what? First terms, x times x is x squared. And then my outer terms, I would have x times negative this guy, the 1 minus 2i, in parentheses. So remember the minus, and you have x times this quantity, 1 minus 2i, okay? And then continuing, and I'm probably not going to be able to fit all this, but I'll try and see if we can squeeze it down. So let me erase this and put minus x times, again, 1 minus 2i. Let's kind of scrunch that down a little bit. So when I go to my inside terms, I'm going to have this negative times this 1 plus 2i, that quantity, times this x. So I'll have minus x times, again, this quantity, 1 plus 2i. And then for the last terms, I have this guy times this guy. Now it's negative times negative, so I know it's going to be a positive, okay? And then what I want to do is say that I have what? 1 plus 2i times 1 minus 2i. Well, I know my formula for that. Remember, if you have a plus b times a minus b, this is a squared minus b squared, okay? So in this particular case, I'm just going to write this down here because I'm just going to run out of room. I'm going to say that I have what? The first guy squared, so 1 squared, which is 1, minus the second guy squared. So if I take 2 and square it, I get 4. If I take I and square it, remember, I squared by definition is negative 1. So this would be negative 1. So really you have negative 4 times negative 1, which is positive 4. So 1 plus 4 is just going to give me 5. So I can write this as 5 here, and that allows me to fit everything on my screen. Okay, so now we're going to simplify. Let me scroll down and get some room going and see where we are. So we have f of x equals, I've still got this x minus 1 out in front. And inside, I'm just going to see what I can do to simplify. So let me put my brackets here. So I have my x squared, and then I have my negative x times 1, which is just minus x. And then negative x times negative 2i would be plus, we'll do 2ix. Then moving down here, I have negative x times 1, which is minus x. And then negative x times 2i is going to be negative 2ix. And then lastly, I have my plus 5. Okay, so what we see now is that this will cancel with this. And negative x minus another x would be negative 2x. So let's go ahead and write that. We'd have f of x equals the quantity x minus 1 times, I'll have x squared. Again, negative x minus x is minus 2x. And then we're going to have plus 5. So starting to look pretty good. So let's scroll down a little bit. I know this is tedious, but you have to do some examples of these. So we'll have f of x is equal to, I'll go through and multiply x by everything. So x times x squared is x cubed. And then minus x times 2x is 2x squared. And then plus, we have 5 times x, which is 5x. And then I have a negative 1 times everything. So basically, I'm just going to change the sign of everything here. So I would have minus x squared, and then I would have plus 2x, and then I would have minus 5. Okay, so let's continue now. All we have to do is just combine like terms. So x cubed, nothing to combine with that. I have, let me get some room going here. I have negative 2x squared and minus x squared, so that would be negative 3x squared. I have 5x and 2x, so that would be plus 7x, and then I have minus 5. So we end up with our polynomial function, f of x equals x cubed minus 3x squared plus 7x minus 5. All right, the next type of problem you're going to see is also pretty tedious. So suppose you're given some polynomial function, let's say f of x equals x to the 4th power minus 3x cubed plus 6x squared plus 2x minus 60. And they say find all the zeros, and they give you a complex zero. So let's think about what we know at this point. At this point, we know that the degree of the polynomial is 4. So I know that I'm going to have 4 solutions, right? At most, it would be 4 distinct solutions, but I know that I'm going to have 4 solutions, even if some of them are repeats. Okay. The other thing we know is that we're given a complex zero of 1 plus 3i, so there also has to be a zero of 1 minus 3i, because these come in conjugate pairs. Okay. So I know if I have 2 zeros here, I can get this guy down to a quadratic, and at that point, I can use the quadratic formula, or if I'm lucky, I can factor, or complete the square, or whatever you want to use, it doesn't matter. We know that once we get it down to a quadratic, we're good to go. So there's 2 ways that you could attack this problem. The first thing is, you could write this out as x minus this 1 plus 3i. Okay, that's your factor. Let me make that clear. And then x minus, you have your 1 minus 3i. That's another factor. So you could multiply these two together, get that polynomial, okay? And then you could divide synthetically this guy by whatever that is. And that would give you 2 different quadratics that you could solve with the quadratic formula. So that's one way you could do it. Another way you can do it, and the way that I'm going to do it probably would take a little bit longer, you can use synthetic division, okay, with this guy and with this guy to get it down to a quadratic. So that's the way I'm going to do it, just to get a little practice of working with these guys and doing some synthetic division. So I'm going to start with this one right here, okay? And what I'm going to do is go 1 plus 3i. And then over here, I'm just going to take my coefficients. So 1, negative 3, we've got 6, we've got 2, and we've got negative 60. And I made a little bit of a mistake here because when you work with this, you want to make sure you have a lot of room. So let me actually redo this. So let me come back up here and say that we have negative 3. I'll push that over here. I'll push my 6 over here, my 2 over here, and my negative 60 all the way over here. You need room because these complex numbers, they take up a lot of space. So let me kind of move this down, and then we'll be good to go. Okay, so let me put a bar down here, drop this down, and we'll start. So we'll come back up in a minute. We'll go back and forth. So basically, I drop this down. 1 plus 3i times 1 is 1 plus 3i. Okay, if I had negative 3 plus 1 plus 3i, I just add the negative 3 and the positive 1, which gives me negative 2, and the plus 3i comes along for the ride, okay? Now, where this gets tedious is that you have to multiply now. You multiply 2 complex numbers, you basically have to stop and do FOIL, okay? So we have this 1 plus 3i times this negative 2 plus 3i, okay? So 1 times negative 2 is negative 2. The outer would be 1 times 3i, which is plus 3i. The inside would be 3i times negative 2, which is minus 6i. And then the last, 3i times 3i is 9i squared. Now, remember, I squared is negative 1, so you can really just say this is negative 9, okay? So you have negative 2 minus 9, which is negative 11. And then on top of that, you're going to have 3i minus 6i, which is minus 3i. Okay. So let's erase this. We don't need that scratch work anymore. And so if I said 6 plus negative 11 minus 3i, what is that? Again, you just work with the real parts. 6 minus 11 is negative 5. So this guy's going to be negative 5 minus 3i. Okay, so here comes again the tedious part. We got to multiply. So we have 1 plus 3i times, you have negative 5 minus 3i. Okay, and then we're going to do 1 times negative 5, that's negative 5. We're going to do 1 times negative 3i, that's minus 3i. We're going to do 3i times negative 5, that's minus 15i. If you want to combine these at this point, it would be negative 18i. Let's just go ahead and do that. And then lastly, you have 3i times negative 3i. So that's negative 9i squared. But again, I squared is negative 1. So you're just going to change the sign of this to plus. So positive 9 plus negative 5, or you can think about this as 9 minus 5, that's just going to be 4. So this would be 4 minus 18i. Okay, so now we want to add 2 plus 4 minus 18i. Well, 2 plus 4 is 6. That's all you're going to be able to do there. And then you bring the minus 18i along for the ride. All right, last multiplication. Again, I know this is tedious, but we have 1 plus 3i times, you've got your 6 minus 18i. So 1 times 6 is 6. And then I'm going to do my 1 times negative 18i, which is minus 18i. And then my 3i times 6, which is plus 18i. Okay. Then we have 3i times negative 18i. So we know that's a minus. 3 times 18 is 54. And then you'd have I times I, which is I squared. I squared is negative 1, so just change the sign. So it's just plus 54. Now, 54 plus 6 is 60. Okay. We know that negative 18i and positive 18i, those are going to cancel. So we're just left with 60. We already knew this was a 0, so we knew we wouldn't have a remainder by definition. So we know negative 60 plus 60 is 0, and that is what we would expect, right? To have no remainder or a remainder of 0. Now, once we're done here, we already know that 1 plus 3i is a 0. We don't need it. And we know that 1 minus 3i is a 0. So we're going to use this information to further get this down. So remember, if we go back up here, if you divided this synthetically by x minus this number, you would get this guy right here. These are your coefficients for the quotient, okay? So we're just going to use that. I'm going to erase this. I'm just going to take these guys, okay? So I'm going to take my 1. I'm going to take my negative 2 plus 3i. I'm going to take my negative 5. Let me put that as a minus. So minus 3i. And then I'm going to take my 6 minus 18i. So what we're going to do is now take the other 0, the 1 minus 3i, because we know that's a 0. And basically, when I take this quotient and divide it by this, I'm going to have a quadratic that I can then solve, again, with the quadratic formula, or factoring, or something like that, and I'll have all my zeros. Okay, so let's bring this down and say we have a 1. So again, 1 minus 3i times 1 would be 1 minus 3i. Okay, so when we add these, you've got negative 2 plus 1, which is negative 1, and then positive 3i minus 3i is 0. Okay, so it's just negative 1. Then 1 minus 3i times negative 1, just change the sign of everything. So this would be negative 1 and then plus 3i. Okay, we add. Negative 5 plus negative 1, or negative 5 minus 1 is negative 6. Negative 3i plus 3i, that's 0. Okay, so now lastly we have 1 minus 3i times negative 6. Again, I can just multiply each term by negative 6. So this would be negative 6, and this would be plus 18i. So again, we knew this was a 0, so this comes out to be 0 exactly, okay? And these would be the coefficients for your polynomial function, okay? That's your quotient. Now, this is going to be of degree 2 now. We started with a 4th degree. We did 1 synthetic division, so it was a 3rd degree. Now we did another one, so it's a 2nd degree. So this guy is going to be the coefficient for x squared. Then this is x to the 1st power. Then this is your constant term, okay? So this guy right here is what we're looking for. So I'll drag this up here. And we'll come here and we'll just say, okay, where does this guy equal 0? Okay, and we can solve this with factoring. Put an x here and an x here. Give me two integers that sum to negative 1 and give me a product of negative 6. Well, you could do negative 3 and positive 2. You could do negative 3 and positive 2. So obviously, if you solve this, you would get x is equal to 3 or negative 2. So I can just add this to my list here and say that another 0 would be 3 and another one would be negative 2. I know I said 0 here. This should be zeros. But when I started, it was singular. We just had 1. So let me just mark this out and say these are the zeros, okay, plural. So we have our 1 plus 3i, which was given to us, our 1 minus 3i, which is the conjugate. And then we have 3 and negative 2, which we found. In this lesson, we want to talk about Descartes' rule of signs. So as we continue to talk about finding the zeros for a polynomial function, we're going to come across the topic of Descartes' rule of signs. So basically what this is going to be is just another tool for us, and it's going to help us to narrow things down a bit. So it's going to tell us the possible number of positive and also negative real zeros for our polynomial function, given that the polynomial function we're working with meets certain criteria. So basically, you want to make sure that the function you're working with has real coefficients and also has a non-zero constant term. So if you have that met, then basically you want to just start out by writing your polynomial function in standard form. So for this example, we have f of x equals, we have 2x to the fifth power plus 3x to the fourth power plus 7x cubed plus 5x squared plus x plus 15. So this is already in standard form. Our term with the highest exponential power is all the way to the left. Then you have the next highest exponential power, so on and so forth. All right. So once you've done all that, you're ready to calculate the number of possible positive real solutions. Okay. So the way you do this is you're going to count the sign changes. So I'm going to put a plus there for emphasis, and I'm going to say from here to here, there's no sign change, right? Positive to positive, sign's the same. Same, 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 right? So there's no sign changes at all, right? It doesn't change. So that means there's 0 sign changes. So we're going to put a 0 here. And that means there's 0 possible positive real solutions. Okay, so that's what that means. Now, if it's not 0, okay, then what you want to do is you want to say you can have that number, or you could subtract away 2 from that number until you get to 0, or you can't subtract away 2 anymore. And we'll see an example in a moment of what I'm talking about there. But for right now, there's 0 sign changes, so there's 0 possible positive real solutions, okay? Now let's talk about negative. So for negative real solutions, what you're going to do is plug in a negative x everywhere there's an x in your function. Now, I'm going to give you a little shortcut for this. Don't go through and actually start plugging things in, because the sign is only going to change when you have an odd exponent, right? So here, here, and then this is the first power, so here. If I think about it, I'm really just plugging in -1 times x. So just think about the -1 part. -1 raised to an odd power is going to give you back -1, so it's going to change your sign, okay? But if I had -1 raised to an even power, like -1 raised to the fourth power, it becomes 1, right? So no sign change. So I'm going to go through and change the signs of, again, the terms with the exponents that are odd. Okay, so this would be -2x to the fifth power. No change here. And this would be -7x cubed. No change here. And this would be -x, and then plus 15. Okay, so now we have a lot of sign changes. So we go from here to here, so that's 1. Here to here, that's 1. Here to here, that's another one. Here to here, that's another one. And here to here, that's another one. So we went from negative to positive, so that's 1. Positive to negative, that's another one. Negative to positive, that's another one. Positive to negative, that's another one. And negative to positive, that's another one. So you got 1, 2, 3, 4, 5. So we're going to put a 5 here for the possible negative real solutions. Now, here's where this gets a little bit tricky, okay? When you think about the imaginary solutions that are possible, or the non-real complex solutions, remember they come in conjugate pairs. So right now, if this was the scenario, you would have 0, because this is a 5th degree polynomial, right? So you're going to have 5 solutions. Again, some of those could be repeats, but you're going to have 5 solutions or 5 roots or 5 zeros, however you want to say that. Now, there's other scenarios that could be possible. Again, when I talk about this, you're going to decrease this by 2, whatever these numbers are, because again, the complex solutions or the non-real complex solutions, the imaginary solutions are going to come in conjugate pairs. So I'm always going to have 0 here, but this could be reduced by 2. So I'd put 3 here, and now I'd put 2 here, because again, if I have 1 solution there, I've got to have 2. It can only be 0, 2, 4, 6, 8. It's got to be some even number. Now, if I decrease it again, this would still be 0, this would be 1, and now this would be 4. Okay, so notice how the total in the row is always 5, right? The total is always 5. So that's what you're looking for. So I started with 5, I went down to 3, then I went down to 1. Started with 0, went up to 2, went up to 4. Okay, now notice how I can't decrease this guy by 2 again, because that would tell me that I have -1 negative real solutions. That's nonsense, right? That's not possible. So you need to keep going and reducing by 2 until you hit 0 or something that's not possible, like in this case right here, okay? So for this example, we have one scenario where you have 0 positive real solutions, 5 negative real solutions, and 0 imaginary solutions. Or you could have 0 positive real solutions, 3 negative real solutions, and 2 imaginary. And then lastly, you could have 0 positive real solutions, 1 negative real solution, and then 4 imaginary solutions. Let's take a look at another example. Once you do these a few times, it's very, very easy. So again, if I want to find the possible number of positive real solutions, I just look at f of x. I make sure that, again, all my coefficients are real, and then I have a non-zero constant term, which I have. You'll notice here you're missing x to the third power and x to the first power. That's okay. You don't have to worry about that. Just as long as you have this guy right here, your non-zero constant term. All right, so it's in standard form. So I'm just going to count my sign changes. So I go from plus to plus, no change, plus to minus, 1 change. So that tells me this could be 1 right here, okay? Now, this is a 4th degree polynomial, so I know there's more stuff coming, okay? So let's erase this, and let's think about f of negative x. Would anything change? No, because this is even and this is even. So a negative 1 to the 4th power or a negative 1 squared, okay, would give me positive 1, no sign change. So this is 2x to the 4th power plus 7x squared minus 4. So it's going to be 1 sign change again. You go from positive to positive, no change, positive to negative, 1 change. So really what we find here is that there's only one possibility because, again, this is a 4th degree polynomial. This row here has to add up to 4, so this has to be 2, right? Again, these come in conjugate pairs. So the only possibility is that you have 1 positive real solution, 1 negative real solution, and 2 imaginary solutions. All right, let's look at another one. So we have f of x equals 2x to the 4th power minus 13x squared plus 6. So again, I have a non-zero constant term, and then I have real coefficients, so I know I can use this. So again, just count the sign changes to get the possible positive real solutions. So this is plus, so going from here to here, that's 1. Going from here to here, that's 2. So I'm going to put a 2 there. And again, I know I can decrease that by 2 and go to 0. So I can either have 2 positive real solutions or 0 positive real solutions. For the negative real solutions, remember, if you plugged in a negative x there, if I plugged in a negative x there, nothing would change because this is even and this is even. So you'd have 2 sign changes again. So let's go ahead and put 2 here and 0 here. But you have another 2 scenarios that you have to consider. So you could have 2 positive real and 2 negative real. And of course, because it's a 4th degree polynomial, you'd have 0 imaginary. You could have 0 positive real, 0 negative real, and then you'd have 4 imaginary. Again, the row has to always sum to 4. Then the other scenario would be you could have 2 and 0, and this would be 2. So 2 positive real, 0 negative real, and 2 imaginary. And then the final scenario would be that you have 0 positive real, 2 negative real, and 2 imaginary. So again, when you go through the different possibilities, you want to think about the imaginary as being what's left over. Okay, so in this case, you have 2 positive real, 2 negative real. So there's nothing left over because you're going to have 4 solutions because, again, this is a 4th degree polynomial. Okay, so this guy, 0, 0, and then you get 4, right? Because there's nothing here. It's got to sum to 4. 2, 0, and then this has to be 2. 2 plus 2 is 4. 0, 2, and then again, this is 2 because 2 plus 2 is 4. All right, let's just look at one final example. So we have f of x equals 6x to the 5th power plus 3x to the 4th power minus 50x cubed minus 25x squared plus 16x plus 8. Again, I've got my non-zero constant term. All my coefficients are real numbers, so I'm good to go. So how many sign changes do I have? So no sign change, then I've got 1. No sign change, I've got another 1, and no sign change. So this is going to be 2. So let's put 2 here. And then we know it's also possible to have 0. Now, if I change this to a negative, okay, think about what would swap. So this would swap because it's odd. This would swap because it's odd. So let's put a plus there. This would not change. This would swap because it's odd. And this would not change. Okay. So now sign changes, you have 1. You don't change there. Then you'd have another one. Then you don't change there. Then you'd have another one. So you have 3. Or you could have 1. So to go through the different possibilities, again, this is going to be a 5th degree polynomial. So I know that my solutions have to add up to 5. So 2 plus 3 is 5 already, so this would be 0, right? 2 positive real, 3 negative real, so 0 imaginary. If I had 0 and 1, well, this would have to be 4, okay? Because again, it's got to sum to 5. Now, other possibilities, I could have 2 positive real, I could have 1 negative real, and then I would have to have 2 imaginary. Again, 2 plus 1 is 3, 3 plus 2 is 5. And then the last possibility is that I could have 0 positive real solutions, I could have 3 negative real solutions, and then I would have to have 2 imaginary solutions. In this lesson, we want to talk about the intermediate value theorem. We also want to look at the upper and lower bound rules. All right, let's start out with something that's very simple. It's known as the intermediate value theorem. And basically, this can help us to determine if a 0 lies between 2 numbers. So what we do is if we have f of x, again, some polynomial function with only real coefficients. And let's say we have 2 real numbers. For simplicity, let's just call them a and b for right now. So if the values f of a and f of b are opposite in sign, then it must be true that at least one real 0 occurs between a and b. Now, if you're scratching your head when you hear that or when you read that in your textbook, I promise you in a second you're going to understand. This is a very, very intuitive concept. So let's say we start with something like f of x equals x cubed plus 2x squared minus 5x minus 6. Now, I'm just going to tell you that there is going to be a 0 that occurs between -2 and 0. So between these two numbers, between -2 and 0, there will be a 0, meaning there's some value that I can plug in for x, and the result of the function, or the function's value, if you want to say that, would be 0. Now, to prove this, in this particular case, it's going to work out to where you're going to have one of these guys going to be negative and one's going to be positive. So in other words, f of -2, if I did that, what will we have? Well, this would be -2 cubed plus 2 times, you'd have -2, and that would be squared, minus 5 times -2, and then minus 6. Okay, so we know -2 cubed is -8. We know that -2 squared is 4. 4 times 2 is 8. -8 plus 8 is 0. So you can just erase this. Basically, what you have here is -5 times -2, which is 10. 10 minus 6 is 4. So this is a positive 4, right? So the function's value when x is -2 is 4, okay? I can also write this as an ordered pair and say that -2, comma 4 is on the graph of this function. Now, we also want to look at 0. So f of 0 is equal to what? Well, I know if I plug in a 0, this is gone, this is gone, this is gone. I'm just left with -6. So on the graph of this function would be 0, comma, -6. Okay. So what I told you was that if f of -2 is a positive number and f of 0 is a negative number, well, then there must be a 0 between these two numbers. So there must be a 0 between -2 and 0. So graphically, we can prove this. If we go back and look at this point, so we had -2 comma 4. So this is my -2 comma 4. And then also I had 0 comma -6. So that's my 0 comma -6. Well, think about this logically. The value of the function here is 4. And let me use a different color because that doesn't show it very well. So this is 4, right? And then the value of the function down here is -6. So -6 there. Okay. Well, in order for me to get from here to here, as I move to the right, notice that every y value between 4 and -6 is going to occur. And that y value includes a y value of 0, right, where we cross the x-axis. And when we cross the x-axis, that's our 0 for the polynomial function. It's going to end up happening right there at -1 comma 0. So that's how this guy works. If you plug in one number and you get a negative, and then you plug in another number and you get a positive, well, then there's a 0 between those two numbers. Now, what you don't want to think here, and this is a common source of confusion, let's say, for example, you plug in and you get a positive, and then you plug in and you get a positive again with a different number. Well, that doesn't necessarily mean there's no 0 between them, okay? It's just true that if it's positive and then it's negative, or you get negative and positive, whatever it is, if there's a sign change, then it must be true that at some point you're going through the x-axis, so you will have at least one 0. Let's look at one more quick example of this. It's a very easy concept. Usually the problems you see with this, they'll just give you two values and say, hey, prove that there's a 0 between them. So all you need to do is say, what is f of negative 6? And this is going to be what? Negative 6 cubed is negative 216. Then plus, you would have negative 6 squared, which is 36. 36 times 14 is 504. Then plus, you'd have 59 times negative 6, which is negative 354. So I'll just put minus 354. And then plus 70. So if you go through and do the addition here, negative 216 plus 504 is 288. If I subtract away 354, I get negative 66. Then if I add 70, I get 4. So let's just say the value here is 4, right? So 1 point would be negative 6 comma 4. Okay. So the other one, let's look at f of negative 4. So what would that be? Negative 4 cubed is negative 64. Then you'd have plus negative 4 squared is 16. 16 times 14 is 224. Then plus, you'd have 59 times negative 4, which is negative 236. So I'll just put minus 236. And then you have plus 70. Okay. To do this quickly, I know that 70 minus 64 is going to be 6. So let's just get rid of this and put a 6 here. And I know that negative 236 plus 224 is negative 12. Okay, is negative 12. And I can quickly do negative 12 plus 6. That's going to be negative 6. So this guy is positive. This guy is negative, right? So 1 point would be negative 4 comma negative 6. So because we go from positive to negative, I know that there's going to be a 0 between those two numbers. Again, my y value here is positive 4. My y value here is negative 6. So at some point between an x value of negative 6 and an x value of negative 4, I'm going to have to cross the x-axis or get a y value of 0. All right, so now let's move on and talk about the upper and lower bound rules. These rules are helpful, again, to just narrow things down. When you're working with finding the zeros for a polynomial function, you have to have as many tools as you can get, especially if you don't have a graph or you don't have, a calculator or something to use to help you out. You've got to just narrow things down as quickly as you can in order to not spend hours and hours and hours trying to find zeros. All right, so if we have a polynomial function f of x with real coefficients and a positive leading coefficient, okay, let me say that again, a positive leading coefficient, then if we divide f of x by x minus k, and your k that you're working with is positive, if each number in the last row of your synthetic division is either positive or 0, then you can say that k is an upper bound. This just tells you that you're not going to have a 0 that's above that. Okay, you can stop looking. So if you had a list of values like you generate with the rational roots test, and you test something in the middle, you take a positive value in the middle of the range, and let's say you find out it's an upper bound, well, you can cut off a lot of numbers, and you can start working down now. All right, so let's see this with this guy real quick, and then I'll show you about the lower bound in a minute. So basically what we want to do is just do some synthetic division. So I put a 5 here. And I'm just going to take my coefficients. So 1, negative 4, negative 2, negative 3, negative 1, and negative 1. Okay, so let's scroll down to get some room. And basically what we're looking for is that this entire bottom row has to be either positive or 0. Okay, if you have any negatives involved, you have to stop. Okay, it didn't work. So this guy's going to come down. So you have 5 times 1, that's 5. Negative 4 plus 5 is going to be positive 1. And then 5 times 1 is 5. Negative 2 plus 5 is positive 3. 5 times 3 is 15. Negative 3 plus 15 is 12. 5 times 12 is 60. Negative 1 plus 60 is 59. 5 times 59 is 295. Negative 1 plus 295 is 294. Okay, so that's your remainder there. But again, all you're looking for here is the fact that you have a positive number here, okay? And you had a positive leading coefficient. So if all the numbers down here are positive in the final row here, your results, well, then you know that 5 is an upper bound. Okay, it tells you that you don't need to look at anything larger than 5 if you're looking for the zeros of a polynomial function. You would want to start going the other way. Okay, so let me tell you about the rule for the lower bound. So if your k, your number you're doing the synthetic division with, is negative now, and the numbers in the last row are alternating in sign, so it goes positive, negative, or negative, positive. If it alternates like that, 0 in this case can be treated as whatever you want. It can be positive or negative, whatever you need, okay? But if this pattern occurs, then we can say k is a lower bound. So none of the real zeros will be below that point, so you can kind of stop your search. All right, so let's go ahead and crank this one out, and I'll show you that this one does work. So this is -3. We'll have 3, 5, -4 again, 3, and -2. Okay, so this is a negative value. We have a positive leading coefficient. So let's go ahead and try this. So I'll go ahead and drop this down. We'll put a 3 here. -3 times 3 is -9. 5 plus -9 is -4. -3 times -4 is 12. -4 plus 12 is going to be +8. -3 times 8 is -24. -4 plus -24 is -28. -3 times -28 is 84. 3 plus 84 is 87. And then lastly, -3 times 87 is -261. And then -2 plus -261 is -263. So if you had done the rational roots test and you were just checking -3, well, immediately you would say, okay, this is not a 0, but I know -3 is a lower bound because this guy is negative, okay? And if I look at these guys, this is positive, negative, positive, negative, positive, negative. So it alternates here, so I know that -3 is a lower bound. So I'm not going to be looking for any real zeros that are less than -3. Okay, again, the upper bound scenario is where this guy is positive and your whole row down here is positive. In that case, I'm not looking for any real zeros that are above that number. In this lesson, we want to talk about finding the zeros of a polynomial function. All right, so now it's time to take all the things we've been talking about over the last few lessons and apply it to a real world example. So we have f of x equals 5x cubed plus 12x squared plus 54x plus 20. So if you got this problem on your test and your teacher said, find the zeros for this polynomial function, what would you do? Well, there's a lot of different strategies that you can employ here. But the first thing that I would do is I would look at the degree of the polynomial, and we see that it's a 3. So immediately I know that there's 3 solutions. Now there could be repeated solutions, but I know there's 3 solutions. Now, because the imaginary solutions, or again, the non-real complex solutions come in conjugate pairs, meaning there could be 0, there could be 2, there could be 4, so on and so forth. Well, that tells me that there's either 1 real solution and 2 imaginary solutions, or there's going to be 3 real solutions. Now, we can further break this down by thinking about, again, Descartes' rule of signs. Remember, you look at the sign changes with f of x. So this is positive, 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 positive. No sign changes in f of x, so there's 0 real solutions that are positive, okay? So that tells me that all the real solutions are going to have to be negative. And you can verify this by doing f of negative x, okay? And so again, when you do this, don't worry about the x because that part stays the same. It's the negative here that you're thinking about because it's a -1 that gets plugged in that's going to change the sign of that term if the exponent is odd. So there and also there, right? Because -1 raised to an odd power is -1. That changes the sign. So in this particular case, you'd have -5x cubed. This wouldn't change because this is an even exponent, so plus 12x squared. This would change, it would be minus 54x, and then plus 20. Okay, so we see that we have 3 sign changes here. You go from negative to positive, positive to negative, and negative to positive. So 1, 2, 3 sign changes. All right, so that means one scenario could be 0 positive real solutions, 3 negative real solutions, and 0 imaginary. And then again, we decrease that number by 2, okay? So we can have 0 positive real solutions. Decrease this by 2, you get to 1. So negative real solutions, you'd have 1 in that case. And then this right here, imaginary, would have to be 2 now, right? Because the row always sums to 3 because you've got a degree of 3 for that polynomial. All right, so this already narrows things down for me. I know that in terms of real solutions, I'm only looking for negative ones. Okay, so if I do my rational roots test, I can throw out all the positives. I don't even need to look at those. So now let's go to a fresh sheet and let's think about this rational roots test. So it's been a while since we talked about it, so let me refresh your memory. Remember, the polynomial needs to be in standard form, and you want to look at the leading coefficient. So this guy here is a 5. That's the leading coefficient because it's on x cubed. The third power is the highest power for this polynomial, right? This one's the second power, and this one's the first power. So this is the leading coefficient because, again, it's the coefficient on the variable raised to the highest power. So this is where I get my q's from, right? All the factors of 5. Then this, the constant term, is where I get my p's from, okay? Remember, all the factors of 20. So think about the factors of 20. So I'm just going to put p here. 20 is going to be what? It's 1, 2, 4, 5, 10, and also 20. And then for q, again, all the factors of 5, you've got 1 and 5. And I know there's plus or minus in each case, but again, I'm just kind of trying to speed this up. We're going to be throwing out the positives anyway, so I'm just going to write everything, and then I'm going to put a negative sign in front of everything just to make it quicker, because in this case, we don't need plus or minus. We already know we don't have positive real solutions. Okay, so I've got to come up with all the possible p over q's. So I'm going to start with the number 1. 1 over 1 would be 1. And then I'm just going to slap a negative on it. And then we'd have 1 over 5, which would be 1/5. Again, I'm going to put a negative on it. And then we'd have what? I moved down. So now you'd have 2 over 1, which is 2. So it'd be negative 2. And then 2 over 5 would be 2/5. So negative 2/5. And then moving down, we have 4 over 1, which is 4. So I'll put negative 4. And then 4 over 5 is 4/5. So negative 4/5. And then let's talk about, we have 5. So we have 5 over 1. So that's negative 5. And then 5 over 5 is 1, right? So we already have negative 1. We don't need that. So then you'd have 10 over 1, which is 10. So I'll put negative 10. And then 10 over 5 is 2. Again, if I think about this in terms of negative 2, I already have that. Don't worry about it. You can just move on. So we have 20. 20 over 1 is 20. So I'll put negative 20. And then 20 over 5 is 4. We already have that. Again, we're changing the sign to negative 4. We already have that. So again, just so you're not lost, I didn't put plus or minus because we already know that there's no positive real solution. So that's why I only have negatives there. Okay, so let me erase all of this. And now we have a list of potential candidates, okay? So here's what I'm going to tell you to do. And this sometimes works, sometimes it doesn't. We talked about the upper and lower bound rules, okay? In the case where the leading coefficient is positive, which it is here, and you have a negative k, a negative value that you're doing your synthetic division with. Okay, we know that if the bottom row of that synthetic division alternates in sign, we've found a lower bound, right? So there won't be a 0 that is below that value or less than that value. So what I'm going to do, when I think about the integers here, forget about the fractions. I've got negative 1, negative 2, negative 4, negative 5, negative 10, negative 20. So I'm going to pick something kind of in between. I'm just going to go with negative 4. And I'm going to see if it's a lower bound. And sometimes you do this and you end up with a 0. So I'm going to take negative 4 and just do some synthetic division. So I'm going to take 5, I'm going to take 12, I'm going to take 54, and I'm going to take 20. Okay, so let me come back up in a minute. I'm just going to drop this down and see what we get. So negative 4 times 5 is negative 20. 12 plus negative 20 is negative 8. Negative 4 times negative 8 is 32. 54 plus 32, well, 4 plus 2 is 6, and 5 plus 3 is 8, so that's 86. And then negative 4 times 86 is going to be negative 344. 20 plus negative 344 is negative 324. Okay, so although we didn't find a 0 here, we did figure out that negative 4 is a lower bound, right? Because the signs here, this is positive, this is negative, this is positive, this is negative. So they alternate. So again, that tells you if this guy is negative and this guy is positive and these guys alternate, you've found a lower bound. Now, I want to stop here and I want to caution against a common mistake. If you had done this with negative 4 and you didn't find that it was a lower bound, that doesn't mean that it's not, okay? It only says that conclusively you can say if these situations present themselves, so again, a negative, a positive, and alternating signs, then you do have a lower bound for sure. Okay. So let's erase this and let's go back up. Now, I can take negative 4 off. I don't need it. I can take negative 5 off, negative 10 off, and negative 20 because those values are less than negative 4. Okay, so everything that I have now would be greater than negative 4. Now, the next thing I would think about here, negative 1 is something easy to just plug in for. So I would just check that real quick. So all we would see is that, again, if you were plugging in a 1, you would just erase all those x's and you would just straight add the coefficients, right? So if it's -1, the sign of the coefficient would change if it's an odd exponent. So here and here, okay? So if we do this, let me kind of go up a little bit here. This would be negative, and you can get rid of this, get rid of this. This would be negative. Okay, so -5 plus 12 is 7. 7 minus 54 is -47, and -47 plus 20 is -27. So I know -1 is not a 0. So f of -1, let me write that down, it's -27. So I know this doesn't work. But something you can check really quickly is f of 0. So f of 0 is what? This is all gone, it's just 20. Okay, so that takes a millisecond. Now, the reason I did that is because of the intermediate value theorem. All these fractions here, -1/5, -2/5, and -4/5, they're between 0 and -1 on the number line. So, because this guy is positive and this guy is negative, again, the intermediate value theorem tells us that for sure we're going to have a real 0 between 0 and -1, okay? So what I'm going to do now is just clean up a little bit. So let me rewrite these fractions. So we have -1/5, we have -2/5, and we have -4/5, and then we have -2. Okay, but I'm going to work with these fractions because, again, I know that there's a 0 between 0 and -1. Okay, so let's start with -1/5. So if this is a 0, again, we use our synthetic division. So the remainder would be 0 if this is a 0. So I'm going to put -1/5 like this. This is a little bit harder because you're working with a fraction, but if you have a calculator, it's not too bad. So we got 5, we got 12, we got 54, and we have 20. Okay, so let me scroll down and get some room. I'll pop back up in a moment. So let's bring this down. And so -1/5 times 5, we know that the denominator of 5 here would cancel with this guy, which is a 5, okay? So I'd be left with just -1 in that case. So this is going to be -1. 12 plus -1 is 11. Then -1/5 times 11, this would be negative, okay? We know 11 times 1 is 11, and this is over our denominator of 5. So here's where it gets a little tricky. You've got to get a common denominator going because you have 54 plus -11/5. So let's do that over here. So 54 plus, you've got -11/5. And you can just put minus if you want. Doesn't matter. So for the 54, I need a common denominator. So I'm going to times it by 5 over 5. 54 times 5 is 270, right? 50 times 5 is 250, and 4 times 5 is 20. So this would be 270. Okay, so if I subtract 270 minus 11, that's 259. So this would be 259/5. So 259/5. Okay, so now we want to multiply -1/5 times 259/5. So what is that? So -1/5 times 259/5. 5 times 5 is 25, and -1 times 259 is -259. So -259 over 25. Okay, so -259 over 25. All right. So now to do this final addition, we want to multiply this by 25 over 25. So this would be 500 over 25. Okay, so 500 over 25. And 500 minus 259 is 241. So this would be 241 over 25. Now, this is not 0. And so we can say that this -1/5 here is not a 0, right? So it doesn't work. So let me just erase this. And let me put this back to 20. And let me erase this. And let me scooch up here for a second. And let me get rid of this one. And let's go to the next one, which is -2/5. All right, so we're going to repeat this process again. Drop this down. -2/5 times 5. The 5s would cancel. You'd have a -2. 12 plus -2 is 10. Okay, so now -2/5 times 10. You think about 5 and 10. The 10 would cancel with the 5 and give you 2. 2 times -2 is -4. So 54 plus -4 is 50. 50 times -2/5, again, 50 divided by 5 is 10. 10 times -2 is -20. Aha, we found it. 20 plus -20 is 0. Okay, so we know that -2/5 is a 0. Okay, so we want to erase this. Keep those numbers down there. You need them. I'm going to erase this. We don't really need this because we have 1 0, and we're taking it down to a quadratic, so we'll quickly find the other ones. So I'm going to go ahead and say that for the zeros, one of them right now we know is -2/5. Okay, so that's one of them. So the next thing I'm going to think about is the fact that synthetically I divided this by x plus 2/5, right? X minus a -2/5 is x plus 2/5. So the result here is going to be a quadratic. So this would be 5x squared plus 10x plus 50. So where does this equal 0? Now to make this a little bit easier, if you're just trying to find out where this is equal to 0, I could divide everything by 5, so I'm working with smaller numbers, because this is divisible by 5, so is this, so is this. And if I divide this by 5, I get 0 anyway, right? So it's fine. It's not going to affect anything. It's just going to make your life easier. So what I'm going to say is we have x squared plus, this would be 2x plus 10 equals 0. So this right here, again, we're just going to use the quadratic formula. So my a is going to be 1. My b is going to be 2. My c is going to be 10. If I think about this, it's what? X is equal to negative b, in this case b is 2, so -2, plus or minus the square root of b squared, so b is 2, 2 squared is 4, minus 4 times a is 1, times c is 10, so 4 times 10 is 40. This is all over 2 times a, again a is 1, so just 2. So 4 minus 40 is -36. And we know if we pull that negative out, it would be I, right? The imaginary unit. So I can say this is I times the square root of 36, which is 6. So you can put 6i here. And basically you could factor out a 2. Let me erase this. We don't need this anymore. You could factor out a 2. And so you could say x is equal to, put a 2 out here. And then inside the parentheses, you would have -1 plus or minus, you would have 3i, and then over 2. And you can cancel this with this. Okay, so because this is divisible by 2 and this is divisible by 2, again, you can factor that out and cancel and make this more simple. So let's erase these. And so we found our other two solutions, our other two zeros. So one of them would be -1 plus 3i. And the other is going to be -1 minus 3i. So at this point, if you want to stop the video and check these solutions by plugging them in, be my guest, but I can promise you they work. So I know this was a bit tedious, but it's good to go through a harder example. That way, if you get something like this on a test, you know what to do.